2 labs today. Okay. I have to say that I'm so glad that this recently released version of Architecting on AWS includes this section, because this is actually on the exam. It's also sometimes asked about, and they didn't have any prior art for this. There was no discussion of this topic prior to these slides that you're about to see here, which is basically, how do I set up high performance computing inside of AWS, right? And they've had it for a while, but no one was really talking about it. So, you know, high performance computing is obviously focused on, parallelization, like parallel clusters of compute that basically allows you to do like, really quickly and, at a broad scale, just number crunching. That's what we're looking for. Now, a lot of this usually falls under the kind of like MapReduce, Hadoop, Spark kind of arena, where it feels like you're like, you're batching, right? You're doing number crunching. You're doing that level of compute. But this is really just like for businesses that do like massive sets of data and need either near real time or just fast number crunching. So there's a ton of options for this kind of thing, because just to mention this could range from, like let's just here, genomics, GIS, all kinds of stuff related around high number crunching. Now, there's tons of options here to kind of make it so that the compute systems that you have both have fast access to each other, right, across the network, fast compute, can scale or auto scale up and down, but also that all the backplanes involved are fast, like faster networking, faster storage, right? Better parallelization. And note that some things like AWS batch are listed here for that level of kind of like batch processing. So, in terms of like specifics, obviously, since this is compute intensive, someone tell me which of the family types out of the T's, the M's, the C's, the R's, which family type is going to be the one that supports compute intensive workloads? Yeah, the C's, right? Just for compute, because they're going to have a not necessarily faster processor, but that box is going to be designed to have a lower ratio of memory to processing cores, and it's going to be focused on processing. Now, if you're doing, and Arpan, I think that's valid, is that if you're doing obviously something that's based more on GPU based, the G and P series is going to make a lot more sense, right? Now, what's funny is that Amazon will tell you that their G series boxes, like the C6Gs, right, and like T4, Gs as well, those are going to be boxes that are built because of their Gravitron processors. They're going to be great for like forecasting models and fire dynamics simulations. The only catch is just remember that G processor, the C6Gs, they're ARM based, right? So they're not Intel x86. So just something to keep in mind. So there's tons of services here that will support high performance computing. One that is relatively unknown is that one in the upper right hand side known as Lustre. Lustre's been around for a while, has an open source project. It basically allows you to run high performance computing incredibly fast with parallelization against this file system. So think of Lustre as almost like a clustered file system built for high performance computing. The other pieces, I think we're just going to talk about just a little bit. We're going to dive into it. So from a networking perspective, you basically can go, there's a hierarchy of how fast you can go from one direction to the next in terms of like, well, let me just add a dedicated ENI. But we talked about this. Adding a network interface to a box doesn't necessarily make the box faster, because the bandwidth on the box is somewhat dedicated. So you have to pick a box that can support this particular bandwidth, right? Now, then what happens is that then you can add an elastic network adapter, which is different than an ENI. ENIs are just virtual additions, so they're really just kind of management partitions. We're now moving past what this was a basic adapter type. We're now moving into advanced adapter types. This is using SRIOV, which is a technology that I want to say came out like 10 years ago. But basically what it does is it attaches a physical NIC to the network, to the virtual machine. And so now we're starting to get dedicated bandwidth. And as you can see, it goes up to 100 gigabits, which is ridiculous. So it's only supported on certain instance types. So, you know, yeah, you have to kind of read the documentation in order to like find out like specifically what you can run this on. And then the fastest and the craziest is really an elastic fabric adapter. So whereas this one basically does work with the virtual machine, this one bypasses the operating system like correctly, directly. So this one is literally direct access. So instead of like para-virtualized, it's like direct access to a network card. There can only be one instance, and you know there's a bunch of limitations to it in terms of what it support and like how you can route it across the internet, across the subnet. But ENIs are the basic level, ENAs are the next level, and EFAs are the highest level. And so they scale from 10 gigabits to 100 gigabits to 400 gigabits per second. So that's the main thing to remember. And remember, as you go up into faster speeds, there's lots of limitations as to what you can and cannot do with these. So, but this is one way to get high performance computing, is to increase your backplane, and you could do it against all of your instances. Now, this is if you want to have dedicated networking, maybe even still with a distributed system. What's cool is that you can keep going if you want to, and you can actually get it. So by default, Amazon tries to spread your EC2 instances across a bunch of hardware. That way, if a host fails, it'll restart that instance. But if it's part of an auto-scaling group or a web server set or whatever, what will happen is that you'll only lose one out of the, or maybe two of those systems, because it's going to spread your virtual machines away from each other. So there's this kind of anti-affinity to not have your virtual machines all sitting on the same hardware. You can create affinity, which actually forces the systems to kind of co-locate and co-live with each other by creating placement groups. So without placement groups, what happens is they're distributed. With placement groups, instead, is they all go into the, not just the same availability zone, but the same piece of hardware if possible. So, and there's different type of placement groups. For example, you can place them on the, you know, so the same server rack, right? Just to make sure that you can get like, you know, the highest speed possible. Because if they're all in the same physical host, then they actually don't ever have to leave the host to talk to each other. And it's all virtualized networking, which is really fast actually, because it's all just memory at that point in time. So there's cluster placement groups where you place things together. There's partition cluster groups. I'm sorry, partition placement groups, where basically you're spreading it so that they don't share the underlying hardware, but they're still kind of clustered together. So it's like clustered, but there's clusters separated from each other. Let me give you a visual to make sense of this. All right, so in a cluster placement group, everything's placed in the same availability zone on the same piece of hardware. You have to, by the way, launch this all at the same time, because that way Amazon can go grab a box and put all your systems on it. So just know that all, like if you want to launch 20 virtual machines at the same time, they have to be done at the same time if you're going to do a cluster placement group, so they can all be on the same piece of hardware. Now, if you're doing what's called a spread placement group, what you're doing is that you are declaring to Amazon, you're like, look, I know that you kind of do this kind of best effort thing where you spread things out. I don't want you to do best effort. Spread everything out across these availability zones, right? And I don't want a single instance to share any hardware. Because just so you know, when you don't declare this, Amazon tries to spread your hardware out, but if you end up with 2 or 3 boxes on the same piece of hardware, and they don't, it's like best effort. They're not going to force that to happen. With a spread placement group, you're saying, look, these things are so critical, they cannot live on the same piece of hardware. We cannot withstand a failure. And then the third one, so we got cluster where it's all on the same. We've got spread where it's all forced to be on disparate hardware, underlying hardware for your virtual machines. And then we've got, excuse me, like cluster placement, I'm sorry, partition placement groups. And so with this one, it's interesting because it divides your systems into partitions and then spreads those partitions out. So things like Cassandra, HBase, where there's like local systems that are going to talk to each other, but they're actually part of a bigger cluster. These are the kind of like software where that makes sense. HDFS, Apache HBase, Cassandra. It's where you're actually got clusters inside of clusters of data, like for example, Cassandra, like a data store, and you want to keep those on separate hardware, but you want to keep the clusters together. So you've got like a mini cluster inside of a bigger cluster, which is what these 3 boxes are here. But you want the clusters to stay on the same hardware, but you don't want all of the clusters to all be on the same hardware. So you don't want all 9 of them on the same physical hardware, but you want 3 on one piece of hardware, 3 on another piece of hardware, and 3 on another piece of hardware. So this basically allows you to create disparity within your cluster, but the mini clusters can all stay on the same box. In summary, the cluster placement group is really just to keep everything on the same piece of hardware. There's very little redundancy if that hardware goes down, obviously. Really high network throughput, really low net latency, because everything just pretty much happens in memory. With a partition group, you're saying, look, I need to push everything away from each other. Nobody can be on the same piece of hardware. And with a spread placement group, you're saying, look, I want to push everything off to the same hardware, but instead of single boxes being pushed off to different hardware, I want you to push these little mini clusters off to different hardware. So this you would only ever discover if you actually read the documentation before. So there you go. You've now heard the terms cluster placement group, spread placement group, and partition placement group. Any questions? Okay. Now, the last section for this is actually just AWS Lambda, which is part of the whole application tier of like, hey, we've got virtual machines, we've got containers, and we've got what's called serverless, or sometimes known as functions as a service. So Lambda is functions as a service, which basically is just snippets of code that can't run longer than 15 minutes, but they can be chained together, and they are really good for event-driven architecture. Now, the cool thing about serverless computing is that when you're using virtual machines, you have to manage the servers, specify the size, and you pay for the capacity that you've asked for, not the capacity you're using, the capacity you asked for. So if you ask for a 16 core, 64 gig system and you're only using 10% of it, you're going to pay a 100% for a 16 core, 64 gigabyte virtual machine. Now, with serverless computing, that changes things because you just tell Google how much memory and compute, and they're usually tied together, your program requires. And then you tell it a few characteristics, like what services is it going to access, what's the trigger. You upload your code and you're done. Like you don't have to do anything else to manage it. If it wants to run 1 million times for 100 milliseconds, Amazon handles all that for you. If it needs to run 10 million times over the course of, whatever, a month, and it needs to run for 500 milliseconds, that's fine. In other words, you're going to pay for how frequently and how long it runs based on what size it's at. So there's 3 dimensions there, right? How frequently is it running? How big is the application, right? How much memory did you ask for? And how long is it running for, right? So if it runs 1 million times, you've asked for 128 gigs of memory, and it runs for a full second, that's what you're going to pay for, is you have to do the math to multiply that. Now, the cost per millisecond is like, I don't know, millionths of a penny or something like that. It's like 1/100,000ths of a penny. So Lambda is actually really cost efficient if you don't have a 24/7 running infrastructure that's constantly being hit, right? But even for event-driven infrastructure, it's remarkably efficient. So Lambda is pretty good at this. So since this is serverless compute, what you do is you just upload your code, and there are various runtimes supported. Now, just so you know, you can create a custom runtime for things that aren't officially supported if you want to. But it can only run for a max of 15 minutes, and it supports up to 10 gigs of memory, which is an improvement, a vast improvement, because it was 1.5, and then it was 4, and now it's 10 gigs of memory. So a single process, a single function, a single code execution can have 10 gigs of memory space. I don't even know how many processors that is, but excuse me. And so notice there's an event source listed right on the page to the left of Lambda. And that event source can invoke Lambda, or you can set Lambda to run on a timer, or you can have Lambda poll event sources. So currently it does support Node.js, Java, C#, Python, Go, Ruby, and PowerShell. And inside the code bundle that you submit to Lambda, you're going to have all of your dependencies. So, and when the event source triggers Lambda, it will submit event information like, hey, I just got a file in S3, or someone just made a change to DynamoDB, or someone just opened up a port on a firewall on a security group out to the entire world. So, and then Lambda will run as a role. So you may remember users, groups, and roles from yesterday. Lambda will run as a role that you give it permission to run as. So if you want Lambda to access other services, that role, the execution role, or what they call the run role has to have access to the services you want. Now, you might say, well, what can Lambda be triggered by? Honestly, directly, these things that are listed here. I will say that CloudWatch has an events function that pretty much allows it to be like, you can trigger pretty much off of anything. AWS config isn't listed here, but CloudWatch events can receive state changes from almost any service. And so CloudWatch on the upper left-hand side, that actually can trigger from a bunch of different sources. So you could actually trigger CloudWatch events, which in turn can trigger Lambda, which people sometimes do because there's not direct integrations with everything here. Notice that Alexa is on the upper right-hand side. I used to have it set up to where I could spin up infrastructure using Alexa, but yeah, it became a security problem for reasons, for teenage reasons. Notice also on the lower left-hand side, there's a service called Step Functions. Step Functions allows you to orchestrate workflows using Lambdas, using an overall workflow orchestrator, which is what Step Functions is. So Step Functions is a workflow orchestrator, which is incredibly powerful for like putting together your Lambda code into a series of event-driven executions. So people have run their entire websites out of S3 and then using Lambda as the kind of like executor for like database calls and whatnot. Data processing, chatbox, Alexa, those are all pretty legitimate like reasons. People also use it, by the way, for MapReduce and triggering batch and policy engines, like enforcing like firewall closures if someone tries to do something illegal. Really anything that you could use a snippet of code for. So like here's a simulated slot browser, like slot machine browser game, right? So this Lambda function, by the way, generates a random result every time there's a slot pull on the website, and then it returns the file names of the images to use as a result. The images are stored actually in an S3 bucket that's configured to function as a static web host for everything. So just know that this is actually directly from the SDK for JavaScript. So you could literally find this inside the SDK for JavaScript version 2, the documentation.
Got a couple of questions about Lambdas. We have a second.
Sure.
So there's the 15 minutes thing. I never understood exactly what happens when and if that 15 minutes is hit. Like, what does the Lambda do?
It's cut off. It's just shut off. Think of it like a power off.
Okay, so it really does just completely fail it. And then would you be able to set something up to know when it's reached that, or is it's just it's done? So it sends
a trigger and says, hey, by the way, 60 seconds, right? It sends, you can actually poll the time left on the execution time. So,
okay.
Yeah, you can set a trigger that says, hey, when this hits, whatever, 30 seconds out, please do the following, right? Which is what most people do with their Lambda code. If they think they're going to run into the 15-minute execution limit, they'll set a poll timer that says, hey, what's the time? Okay, when I hit 30 seconds, please do the following, write everything, all the data out, put the logs out, and then prepare for shutdown, right?
Oh, wow, that would have been so helpful in the project.
Yeah.
And then you said for step functions, you said they're good for workflow something. I didn't catch it.
It's workflow orchestration. So if you're like, hey, I want to process an image. So an image hits an S3 bucket. And actually, let's say it's a video. Video hits an S3 bucket. And what happens is that immediately, maybe it hits SNS, which is the notification service, and that kicks off like 3 Lambdas. Now, instead of doing like all that orchestration with SNS and all this other stuff, instead it could also just kick off a step function. The step function would then say, oh, we got a video file. What we're going to do is we're going to make a desktop version, 2 mobile versions, and some other version. Like a transcoded version just for audio only. And it would kick all that off, and then it would be like, okay, did the file write? Yes, great. If it didn't, go back and check and see if we can run the file again. Okay, it's like those kind of conditional like logics where you're like, you want it to do a bunch of different things, and there's like more than one Lambda function involved in it. Those kind of workflows is what step functions does. So it allows you to orchestrate the pathing, the parallelization, consecutive or kind of like serial kind of execution of Lambdas. It lets you to orchestrate a workflow with a bunch of different Lambdas involved.
Okay, both those 2 questions answer why the last architecture I worked on was very confusing. Thank you.
Yeah, you're welcome. Yeah, so step functions is pretty much considered a staple now, especially now because it's like super. It wasn't super stable when it first came out for a couple of years ago. But now it's considered pretty much a staple for when you're working with Lambda. If you want to orchestrate workflows and have conditions and triggers, and you want to like walk them through a user journey that has a bunch of different Lambdas in it, it's pretty much the thing you use. Yeah.
Cool.
Good.
My quick question. So on Lambda, you're saying like it can be invoked for a time, right? For 5 minutes, and then after some time invoke it for another 5 minutes. It's something like that.
Well, 15 minutes is the max. It was 5 minutes, but now it's 15. So it's 900 seconds now. But you don't have to run it for 15 minutes. You can run it for as long as you want to. So if you only want to run it for 100 milliseconds, you can do that. But 15 minutes is the maximum execution time.
Okay. And if the processing is happening, whether it will stop that processing at that time?
Oh yeah, no, it'll cut off at the knees. It's just done.
Okay.
It's like it's got powered off. At 15 minutes, it's just going to stop it.
Okay.
Yeah. So that's what with Haley, we're talking about, like you want to probably be aware of the time. If you feel like you're getting to you're going to run to 15 minutes, you can actually set it to pull the time and say how much execution time is left. And so at like 30 seconds or 60 seconds left, you could say, hey, I need to dump my logs. I need to write all my data out. The way a lot of people do it, by the way, is that if they're processing data with a Lambda function, they'll have it checkpoint, right? Like every time it finishes a batch, it'll write data out and then continue and then write data out. And it'll just keep going until it hits the 15-minute execution time.
Okay, so just check it, and if it's near to that 15 minutes or whatever time you said, then don't process the next batch.
Right, or the next batch will just fail. And since the data hasn't written, if you start the next Lambda function, the next Lambda function might go check your external data store and say, what was the last batch written? And then pick it up from there, right? That's another way to do it, is just have the record of execution be in the external data store. So when the Lambda function starts, it goes and checks the data store and says, hey, what was the last thing that was executed? Oh, batch number 112. Okay, great. Now I'm going to start with 113. So it's going to go through, right? So that way you don't really care if the Lambda fails or not. It'll just keep going and you just keep checking the data store for progress.
Okay, got it. Thank you.
Yeah.
Michael, I have a question that based on some of the experience I've had with some of the people that work at, and my LOB at Travelers, they've been starting to use Lambda a lot now, and they just basically stick an API gateway in front so they can use it as an API.
Yep.
And don't ever justify why they're doing this, because you can always do the same thing with, say, a container, right? Just call it something that's containerized, which is kind of also, I guess you can call it serverless if you let Amazon for you, with that whole Fargate stuff.
Right.
So I know all of this stuff is possible, you can even spin up an EC2 instance, put it on your web server, and, or app server, whatever, and do that thing as well. But then you kind of manage it. But I'm just wondering, Lambda, why you would choose one over the other, given that they're both technically serverless and you kind of pay as, I think you pay as you go, as like you said. So I know it's a pattern that AWS does advertise, is backing your APIs, but I'm just wondering why you would ever choose this over something else that AWS provides, like containers.
Well, containers, like for example, you could run your application inside of a container, but you wouldn't have an API gateway in front of it. So API gateways add a whole series and set of functionality that you don't get with just running an application, including metering, rate limiting, caching, version control. The API gateway service is like a MuleSoft or God, what are those other services? Like Red Hat has one, but it's an API lifecycle management tool. Basically, is what it tries to be at a very simple level, not as sophisticated as like a MuleSoft, but close. And so API gateway put in front of anything, whether it's a container on the backend or Lambda, is going to add a whole set of functionality that you can't replicate. But taking that out of the equation, your question really, it sounds like, Alex, is like, okay, well, great. So we can put API gateway in front of anything. So why would we host it in Lambda versus running it in a container? So on AWS specifically, obviously, if you wanted a 24/7 running, application, my general recommendation is stick it either into a container or a virtual machine, preferably a container. If it's an event-driven architecture that's only going to be accessed occasionally or whenever the API gateway, for example, is hit and it doesn't need to run 24/7, then I would use Lambda for that. But it also depends, because not everything can fit into Lambda, because Lambda does have memory and execution limits. So for example, if you need something that's going to run for 20 minutes, if you can't orchestrate that out, then it can't fit into Lambda. It's going to have to fit into a container. So that's really the execution time is one of the great delineators. But I also want to say this, is that while containers are cheaper than virtual machines, and I'm a Kubernetes advocate, right? So I work mainly in cloud, well, really AWS and Kubernetes. Those are the two things I mainly do, other than business transformation, which is really weird. So the problem is that containers compared to Lambda are typically more expensive, even with Fargate, because with Fargate, what you're saying is that I don't want to pay for a virtual machine. I just want to pay for the size of my container. But as long as that container is running, you're paying for it. With Lambda, you're only paying if someone is executing against it. So it really is a very different, because a container is the capacity charge, and then really Lambda is utility charge. Now, I say that if you're executing Lambda a million times an hour, that might be more expensive than running a container. So you really have to do the math to see. But in general, Lambda ends up being cheaper. But those are really the two questions you have to answer. Is one, how long is my process going to execute a single workflow for a user request? If it's more than 15 minutes, you have to use a container. The other thing is cost-wise, it's going to be cheaper and more operationally effective to use Lambda, but only in a lot of use cases. You might have an edge use case or a container might make more sense.
Right. So pretty much at the end of the day, you kind of have to do the math. Sounds like to
Always.
Figure, where do these charts intersect and when does one become cheaper than the other?
Yeah. In general, Lambda will be cheaper, but the other thing is that whatever the team's familiar with is probably the tool they should use. That's the other thing. I walk into people, businesses all the time, and they're like, we want to switch over to serverless. And it's like, okay, well, how do your developers feel about that? And they're like, we don't know. We didn't ask them. We just need to go there. It's like, okay, well, then who suggested that we go to serverless to begin with? And they were like, well, we saw it at a conference. And it's like, okay, now we're having a different discussion, right? There's no business driver here. You just saw something at a conference and now you want to change the technology, but you haven't talked to your people to see if they're excited about it, right? Yeah. But
Apps for you. Those are good questions.
yeah, those are good questions. Yeah. And I think we've all been in situations where we just had to go with what the hype cycle declared, right? Everybody's excited about Kubernetes, so we're going to go to Kubernetes, right? Now, I'm a Kubernetes advocate. I love Kubernetes. Been working with Kubernetes for 5 years. Kubernetes is not a panacea. So it's like people start throwing that around and you just kind of have to go with it, right? Because that's what the business has decided they wanted, not necessarily for business reasons. Yeah. But yeah, overall Lambda is going to be operationally easier, generally cheaper. But again, remember the 15-minute execution time. Good. Okay, well, now we're on to a knowledge check. All right. You may remember AMIs from yesterday. Those are Amazon machine images. Which of the following of these are true? This is almost like an exam question. I love it when they do this kind of thing. Really? Only? Yeah. Excuse me. Just to talk about this for a second. This cracks me up. So first of all, AMIs can only be obtained from the marketplace. Well, we saw yesterday that's not true. AMIs can only be used by users within a single account. Only, huh? No, that's not true either. Actually, you can share AMIs with multiple accounts. AMIs can specify the subnets for launch. No, that's not part of what they can specify, so that's out. So then AMIs can include block device mappings that specify the volumes to attach. Yes, right, because you can specify what hard drives you have. And then you can launch multiple instances from a single AMI. That's literally the purpose of AMIs. If you could only launch a single instance from a single AMI, that would be pretty tough, actually. So B and D are definitely the right answers. All right, so here's a good one for the next one. In the instance type name M6G 2x large, which aspect of the name indicates the instance family and helps determine its best use case? What's the most important letter for determining the family type, not the attributes, but the family type? Yeah, so definitely A in terms of M standing for median, right? Let me ask you this. By the way, if you get this like kudo bonus points, does anyone remember what the G stands for? Yeah, the G is an attribute. In this case, it's the Gravitron processor. It's those ARM-based processors that they use. And then Arpan, I think you called out D, which was 6. That's obviously the generation or the version number of the virtual machine. The t-shirt sizing is really kind of arbitrary. In other words, if you see a 2x large and a 4x large, that's just means that the 4x large obviously is 4 times an extra large. But if you don't know what the numbers are, you got to go look them up. And, you know, just to be frank, even we don't memorize those. We go look them up. And Amazon doesn't ask you. They don't. I've never seen in dozens of exams, I've never seen them ask about, hey, what is the size? Like how many processors or how much memory does this have? Okay. Which of the following are true statements regarding Lambda? So remember, elimination is also good as just knowing the answer. Probably the most important things to know about Lambda is the maximum execution time, and of course, what's the maximum size of memory a process can consume, right? So allocated to 10 gigs of memory, 15 minutes. So that's definitely correct. Good. Excellent. Okay. That's the end of module 4. Any questions? Now, yesterday, wait a minute, that might have been too fast. Were there questions? No. Yesterday, remember, just to reinforce this, because this is a kind of a good review for kind of yesterday's lesson in general, is that remember yesterday that we talked about how regions are made up of availability zones, right? And that there are local zones, which are oddly enough, just availability zones, but they're not inside the region. They're actually at another city. And I think we saw there were 13 of those yesterday, which is a big increase from last year's 4, right? Note that in every region, let me say that again, in every region, you must create a VPC if you want to run something with a network card. In other words, if you're running, for example, Lambda doesn't necessarily have to have a network card unless you want to stick it in a VPC. So Lambda runs at a regional level, but virtual machines always have a network card. And so you have to have a VPC with subnets in order for that to function. Now, here's some things that we want to pay attention to. The lab VPC down here, the like mask, if you will, the CIDR mask is a /16. What that means is that this 8 octet and this 8 octet are fixed. This is the network portion of that VPC, meaning anything inside that VPC has to start with a 10.0. That's what that /16 means. By the way, what's the smallest? I'm sorry, I'm going to use some confusing terms here. What's the largest number I can use beyond that /16? Because this is on the exam. You want a /16, what's the largest I can use? Good, Aaron. Yeah, 28. So you're asked if, like, what's the largest a VPC can be? It's either a /16, which oddly enough, the smaller the number, the larger the network. So a /16 or a /28. So any number in between a /16 to a /28 can be used. So that /16 means that this first octet and this first octet are frozen. Everything that's inside that pi must start with 10.0. How do we know? Well, if we look at the private subnet and we look at the public subnet and we look at these first numbers, guess what? They're 10.0. Now, here's the problem. When we create a subnet, we're taking the VPC pi and we are putting it into slices. So when we create a subnetwork, which is a slice of the VPC network, it not only must start with 10.0, but now we're saying, look, this is a /24. So we're going to actually freeze this last octet. So now any host that sits inside this green public subnet is going to start with a 10.0.0. The last number can change because between 0 and 255, although there are some limitations there, but in general, that's true. Notice here, they're doing a /23 with a 2. Now, I'm not going to get into the complication of using a /23 or a 22 or a 21. That's a whole like networking class. But note that everything in here in general is going to have to start with a 10.0.2 in order for it to be inside this network. Okay. So anything inside this private subnet is going to start with 10.0.2. Now, one thing to be aware of, I'm going to clear these drawings out, is that you might be aware that over here on this routing table, it says that, hey, if you're looking for 10.0.0.0/16, which basically says this portion right here, if you're looking for a 10.0 network, this 10.0 network is inside this VPC. Do not leave the VPC to find any network that starts with 10.0. So if the public subnet, if this instance is trying to find this instance, it'll go to the route table and say, hey, by the way, that's local. And then they'll say, oh, it's local. So let's just go back here. In other words, they'll find each other because this entry over here says that these are local networks. Now, let's say that Alex is like, I've started a whole new Pokemon version 4 Go, right? I guess I have my own Pokemon version. And I got servers and they start with a 53 dot whatever, 53.1.1.1. Because that 53.1.1.1 does not match this 10 address, and there's no other entry in here for 53.0.0.0, by default, if this box over here is trying to get to a 53 address, and let me remove some of this to make it clear. If this box right here is trying to get to that 53 IP address, it's going to go look at its route table. And I make it sound like it's a person, but it's not. It's a lot more simple than that. And this is going to say, hey, by the way, 53.1.1 is not 10, but it matches this because that's what this says. This says any other traffic, I want you to go to the NAT gateway. Now the NAT gateway is going to say, hey, 53.1.1 doesn't match anything here except for this. And so the NAT gateway is going to send traffic to the internet gateway, which in turn is going to go out to the internet. Questions? This, by the way, is how a private instance talks to the internet, is it goes through the NAT gateway. But this is why these NAT tables are important.
So Mike, when would you have more than 2 items in the route table when you work with public and private subnet? Because I'm a
Yeah. For example, let's say Arpan that you had 10 subnets on here, but they were in other VPCs.
Mhm.
When they're in other VPCs, that means that this network changes, right? Because it'd have to be a 10.1 or maybe a 10.2, a 10.3. So if you had other VPCs out here, what might happen, let's say there's another network and another network and another network, you would add entries into your routing table that says, hey, if you're looking for this network, go here.
But if you don't, it will still find it, right? Because it will just go to the internet gateway. It might just make a longer U-turn.
No,
per se,
VPCs by default can't find each other.
Okay.
Yeah, VPCs by default can't find each other. You can either peer them together, which is something we'll talk about in module 2, or you can run a transit gateway, which will route them to each other. But by default, VPCs cannot talk to each other.
So in your example, one VPC wants another VPC with a different, provider. What would you put in the routing table? You wouldn't put, that IP address and then local, because it's not local to that VPC. So what would that second attribute be?
All right, so let's say that this was your IP address for your VPC up here, right? So this was this technically, let's pretend this is a VPC. Oops. Not sure why I didn't grab a square, but okay, let's just roll with that. So then what would happen is that down here, probably before you got to the internet gateway, you would put, hey, 10.2.0.0/16 is VPC ID 2.
Oh, the name of the VPC.
Well, it's actually, there's an ID that you have to submit that's a networking ID, which basically says, hey, if you're looking for the 10.2 network, go talk to this VPC. Because remember, inside this VPC, the 10.2 VPC, there are subnets that go 10.2.1 or 10.2.255 or 10.2.250. And so what you're telling is saying, hey, if you're looking for a 10.2 network, just go talk to this VPC. That VPC knows where those networks are.
Okay. That makes sense.
Yeah. So when you peer VPCs together, what you're doing is on both sides of the equation, you are adding a route entry that says, hey, these two VPCs know how to talk to each other. And that would happen for n number of VPCs. So if there's another one that was a 10.3, you'd add a 10.3 that here. If there was another one that was a 10.4, you'd add a 10.4 entry here. By the way, this is a very cumbersome way to do it. That's called VPC peering. Amazon last year or the year before came out with something called the transit gateway, which we're going to talk about, which if you have more than like 300 VPCs, I know that sounds crazy, but it happens. You want to use a transit gateway instead of VPC peering, because with transit gateway, you don't have to manage the routing tables. So for all you network engineers out there, that's what you would want to do instead. The rest of this, did it make sense? Like, for example, one point to clarify is that the internet gateway doesn't really route. The only thing it does is it goes out to the internet and allows the internet traffic in if the firewalls allow it. That's really it. But like if the internet gateway isn't aware that there's other VPCs here, the internet gateway won't do routing unless the traffic is destined for that VPC. So it doesn't do this. Okay, last two questions then before we move on. If I were going to draw a box around something to represent where a security group, which is a stateful firewall, where that lives, what would I draw a box around? Would I draw it around this?
The subnet.
for a security group. So
in the
here,
yeah, in the private subnet.
okay. Now, let me correct that directly because I want to make sure, because I love it when people reveal like what's going on in their heads, is that this is actually a network access control list. So this is a NACL. This is not a security group. So the firewall that goes around the perimeter of a subnet is a network access control list. That's a NACL. That's a stateless firewall. So technically you're correct, it is a firewall, but it's not a security group. For a security group goes around a NIC. So the security group goes around the instance's network card. And you might say, well, what if the instance doesn't have a network card? Let me just tell you, anytime you launch a virtual machine, there's always one network card on it and you can never remove it. You can add more network cards, but you can never remove the last network card off of a virtual machine. You know why? Because if you remove the last network card, then you can never get to that box. So it doesn't serve any useful function at that point. But to clarify, this is a NACL, this is a security group. Okay. Any other questions? You know what the great thing is, just to say this, is that most of the time, we don't have to set up the networking. You know, the only time I ever run into companies that where the people like yourself have to set up the networking is consulting companies, like Booz Allen or companies like that. And I feel for those guys because, you know, unless you're a network engineer, doing this is not something you do often, nor is it necessarily that fun. All right, any other questions? Thank you so much, by the way, for participating. That was spectacular. Okay, wait, hold on. I got one more question that occurred to me before we move on. If I was going to make this redundant, let's say that this was a web server and I wanted to make sure that I followed Amazon's best practices, and this was a web server, which, by the way, we probably wouldn't put a web server on a public subnet. We probably put it on a private subnet, but let's just pretend for a second it's there. What would I duplicate here if I wanted to make sure that that was highly available web server? Yeah, so Alex, sorry, I didn't see the timing on that. I think you typed it just now, but you would duplicate the instance. And in order to duplicate the instance, where would I duplicate it at?
Separate availability zone.
Boom, that's exactly right. So you create another availability zone in the same VPC and you would duplicate the instance. Now, to get traffic to go to both instances, there's something that I'm going to say, we haven't talked about it yet. It's called a load balancer. The load balancer is a device that sits in front of multiple virtual machines or containers. And basically what it does is it allows you to route traffic or distribute traffic to multiple virtual machines or multiple containers. We're going to talk about a load balancer because a load balancer is probably the secret sauce along with auto scaling that makes it so that virtual machines are not as expensive as they are in your data center. So
why did you say that you wouldn't put the web server in the public subnet? Don't you want to get hit with web requests?
Ah, that's a great statement, Alex. I'm glad you're thinking about this because that's exactly right. Because you're like, wait, wouldn't it need to be in a public subnet in order to receive internet traffic? Yes, unless we did this. So let's say I put my load balancer right here. So what happens is that Amazon, by the way, is responsible for defending a load balancer. And I don't want to stick anything on the internet. I don't know, Alex, I don't know if I said to share this with all of you, right? Is that once a year, a buddy of mine, Chris Kelly, who works for another company, actually he got into crypto. It's really weird, odd conversation. About once a year, usually at the beginning of the year in January, we go to his home because he has fiber connections all over the place. And we put boxes on the internet to see how long it takes for them to get hacked. A Windows box with all of the stuff turned on takes 37 seconds to get hacked before it starts spewing messages about, you know, do this and we've encrypted your hard drive and blah, blah, blah. A Linux box usually takes a couple minutes. If we turn on all the firewalling and stuff, it usually doesn't get messed with if it's hardened, right? A hardened Windows box is the same way. It takes longer, but eventually they all get hacked. So I know that sounds weird. People hate hearing that. The internet's not a really safe place. Regardless, so the reason we want that is that you're responsible for defending operating systems that you put on the internet. If I put a load balancer here, and let's say that I've got a customer coming in giving me traffic, right? The load balancer is responsible for distributing traffic, but the only thing that needs to be publicly available is the load balancer. All of the, let's say that my little boxes here are servers. The servers can be on a private subnet. They don't have to be on a public subnet to receive traffic from a load balancer. And so the load balancer stays exposed on the public subnet and everything else is on a private subnet. This is now a standard pattern for
I thought load balancers you put outside of subnets, but you put yours inside.
Well, the way they actually work on AWS is that it's a virtual device. And what it does is it sticks a bunch of network cards inside all of your public subnets. So it actually sticks a NIC inside your public subnets.
Okay, that's really weird because, you know, the way you're making it sound is you'd have two public subnets and two different availability zones, and you'd have a load balancer balancing between the two, which means the balancer has to be outside of the subnets.
And technically it is. So if I were to draw it like accurately as far as like how it technically works, what would happen is that technically the load balancer actually sits more along the lines of at like a VPC level. And what happens is that the load balancer sticks a network card inside every subnet, public subnet that it's actually load balancing for. And so what it does is it actually puts a network card in every subnet that it's like, you know, distributing traffic to. And then what happens is those network cards are the ones that actually like then talk, I'm sorry, to the private instances in this case, right? So technically that's how it works, is the load balancer is a virtual device that's outside, like in the VPC, and it has basically virtual network cards it sticks in all the subnets, the public subnets. You note that you can run a load balancer privately, so it doesn't have to be on the internet. So it will also stick network cards inside the private subnets as well.
So how would you do load balancing if it's across regions then? Would
So
you have
load balancing
another load-
across, yeah, load balancing across regions. It's a great point, Arbon. So you can't use the load balancer for that because there is no global load balancer yet that Amazon has. But like, oh God, I think we kill me for that. Azure has one, for example, right? But here's the catch. AWS has a global accelerator, which we're actually going to talk about in module 2. That global accelerator will actually allow you to route traffic between regions. So it acts as a global load balancer.
Okay.
The other way to solve that is that you can use DNS, but I got to tell you, DNS is a horrible load distribution system. It's a great traffic cop for directing traffic, but it's not great for like guiding and shaping traffic. So the global accelerator we'll talk about later on. Great questions all around. Alex, did I answer your question, or was that just more confusing?
That's a little bit more confusing because it's didn't put these network cards going all over the place. I don't know.
But technically you're accurate. You can just think of it as sitting outside the subnets. So it can just talk to private subnets easily.
Okay.
Now the lab yesterday, did that make sense as far as like the VPCs and creating everything? Did anybody have any trouble yesterday with the lab other than maybe like instance sizes or associating the wrong subnets? Anything to share there? All right, so here's a test question for you that pops up all the time. What is the URL that you want to curl if you want to retrieve metadata against an instance? You can give me any portion of it that you remember.
So VPC, right?
Well, no, if you're inside the operating system on an instance, an EC2 instance, and you need to retrieve metadata about the instance for your script, what is the curl URL? What is the URL that you curl to make that happen?
Curl minus HTTP 169.254. I think you asked us to take that as a test question. I think you're asking that /latest/metadata.
That's it. That's exactly right, Rush. Yeah. So, oops, I just sent that to someone directly. Hold on. Yeah, so here posting in the chat. So that's it. The 169.254, 165.254/latest/metadata. Perfect, Raj. That's exactly right. Just remember that. A lot of people will use that for their scripts when they're like user scripts inside of a box. And some people don't. Some people never use it. It's funny. I find myself having to use it on occasion when I'm troubleshooting inside a box and I'm like, what is your IP address again? And instead of going to the console, I'll just curl it and grab it back, right? But it is very useful if you are using scripting to configure your boxes, even with if it's like Python, Chef, Puppet, or Salt. So good. Okay. Well, it seems like we're kind of done with that module. So let's move on to the next. Hold on. Let's see if I'm still logged in here. Nope. Okay, we'll come back to you. Okay, so I think we are done with 4. So let's talk about storage. Oh, storage is a fun conversation. Okay. We're gonna do an expose into storage, then we're gonna take a larger break. Actually, I might stop in just a minute to give us all a break anyway. But all right, so we're on day 2. So now we're starting storage, database services, monitoring, scaling, automation, and containers, which is tons of fun. By the way, I'm probably going to overwhelm you with free workshops at the end that you can do inside your account. So just know that you can also get extra exposure to a lot of these services, both through Quick Labs, which you have access to, I think, until January 1st, but also some free workshops that are published by Amazon. Okay, here's a question for you around storage. Which statements are true regarding block and object storage? Take a gander for a second. Tell me which of these is true. Excellent, Aaron. How did you know that? Block storage uses a file system hierarchy. That's true. So just to be clear, block storage is meant to be mounted inside of an operating system. So if you hear the terms block storage or object storage, block storage is meant to be mounted inside an operating system. Object storage is not meant to be mounted inside of an operating system. It wasn't designed for that. So object storage actually uses like a database to kind of track objects. That's actually fairly accurate. Block storage writes updates only to change blocks. If you have 100K Word file and you only change a letter in there, all it's going to do is change the block on storage that contains that letter change. It's not going to change the rest of the file unless it forces you to write the whole thing back, right? And then what happens is that if that's on a remote file system like object storage, and I change 100K Word doc, I've got to push that whole file to that remote storage system because it doesn't do blocks for files, right? It's one file, one object. So if you want to update the file, you have to update the object in its entirety. Because remember, object storage isn't mounted on an operating system. It doesn't show up as a drive letter. So the answer is truly E, all of the above. Now, here's where things get a little weird. But you're like, we're used to Michael saying that now. Block storage and file storage are both meant to be mounted under an operating system. The difference is that block storage is like your USB hard drive, your internal hard drive. In other words, it's typically considered to be directly attached, but technically in AWS, it's not directly attached, but just roll with that for a second. Block storage is typically, meant to be directly attached. File storage is usually run over a network, but both file storage and block storage mount inside of an operating system. So they show up as a drive letter, right? Now, mine's a little crazy. You're like, Michael. So here, for example, I can't really make that bigger. See all these drive letters over here? These are all the various like disk drives and storage that I have on my system. Some of these, by the way, are network attached, meaning they are attached to a remote server inside of my house. That's file storage. They're remote attached. They're not directly attached. But a lot of those disk drives were actually block storage. They were directly attached. Now contrast this, say, with object storage. Object storage is a remote system. Now, I have the pleasure, by the way, of still having access to an FTP server, which cracks me up in this day and age. And so if I go and connect to this server, if I connect to this server, if I click upload, is actually a remote system. Like everything on the right-hand side is actually a system located in Canada that I'm actually accessing. Now, if I want to retrieve an object, I got to retrieve an entire video file. I can't just get a portion of it. If I want to push an object, I have to push an entire file. This is not locally mounted. This is a remote system. Not even on my local network. This is like in Canada, right? And so my point to that is that object storage is remote storage systems. And so Amazon has a solution for each of these. They have directly attached disks, they have network attached disks, and they have object storage, which is a remote storage system. So let's talk about what this is. So here's our stakeholder feedback. It's like, look, we've been pushing our storage capacity in our data centers and our budgets for that to the brink, right? And so since we run Windows and Linux, we also want to use shared file systems. So we want to be conscious around cost. We want to expand our storage capabilities. And so we need a full range of block, file, and object storage because one, we want to get more effective with our dollars, but we also need to support all our use cases. You know, our storage demands only expected to increase. How can we transport data to or from AWS? Like, let's say we don't want to use a network for security reasons, or because it would take us, a year to transfer, 100 petabytes of data over to AWS. So AWS, oddly enough, has a lot of offline storage options that you can use to transfer data from them and to them. So we want to optimize storage costs. We want to reduce for the cost of storage for all files as they age, because what if they're not relevant anymore, but we still need to keep them for legal reasons? What can I do to build scalable storage that supports both Windows and Linux? And if I need to move a lot of data quickly and I can't wait a year to transfer 100 petabytes of data over my wire, how can I do that? So here our architecture fleshes out just a little bit more, because notice that the things that are relevant are this, and this. So, and by the way, there's kind of like disks attached to these guys, which we already talked about. So just know that we're not really going to talk a whole lot more about EBS, but we've seen some of that already. All right, so let's talk about some solutions. All right, so let's collaborate to plan some storage migrations. We have lots of storage needs, okay? So in general, just, shotgun, right? There's a bunch of services related to block, file, and object storage. Let me break this down. So in terms of block storage, we've already seen some EBS. In terms of file storage, that's this. And in terms of object storage, that's this. Now, the rest of this, direct connect and transfer acceleration and data sync and all of this could be a class in and of itself. And some of these are indirectly relevant to data security and management. So indirectly relevant. They are directly relevant for data security management, but indirectly relevant for storage. Okay. But this little circle in the center, this is the one that matters the most, right? Wow, that was really badly done. How about I clear my drawings and try again? This in the center, this is what matters the most. Those are the three: block, file, object. So let's talk about those in detail. All right, so you want to reduce the storage of the cost of storage for older images as they age. How can I automate the process? So one thing this presupposes is that you understand that S3 is the object storage service, and S3 has like 6 tiers of data from hot to cold. Now, S3 basically allows you to just dump files. This is the cheapest storage available. And you saw me using the calculator the other day to show the difference in costs between California and, say, Virginia. But one thing you didn't see me do with the calculator is show you the difference in cost between the different tiers of S3 storage. So S3, by the way, is a great potential use case for basically any files that you want to store in mass as cheaply as possible. S3, a terabyte per month of enterprise class storage that has like 4 or 5 nines of availability and 11 nines of durability starts at $23 a month. If you drop it all the way down to the coldest tier of storage, a terabyte of data will cost you $1 a month. Now that tier of storage is not directly accessible, but a copy, a backup of it is available, right? And you can restore it usually within hours, if not minutes, if you want to. Now, S3 functions with this concept of buckets. You can think of buckets as a top level directory. They're really not directories, but that's the best way to think about them. And then what happens is that buckets get stuck basically into folders. In S3 parlance, they're called prefixes. It looks like a folder though. Let me show you what that looks like. Let's go take a look. MFA for the win every single time. Oh yeah, my password's gonna expire. All right, so let's go over to S3. And I know that Travelers uses S3 a lot because I taught classes for it, especially to the data science people. So here are the buckets, right? And so the buckets are the top level folders. Inside these buckets, by the way, are prefixes, but they're listed as folders. So if I look at, for example, this README file, and I look at the URL for this README file, notice that it contains the word Jenkins, which is a prefix / folder right next to the object. The bucket name is right here. So S3 uses the concept of buckets, has its top level folder, prefixes, and by the way, you can have many different prefixes. I could put a dozen prefixes in front of this object, and the object is here. This forms a URL where the bucket name's at the beginning, and then you got the prefixes and the object at the end. So this is how S3 stores an object which is composed of a file and any metadata about the file. Other things to note is that you can control access to these buckets and the objects inside of them. Because remember, when we did identity-based permissions yesterday for IAM, remember S3 required permissions for the bucket and for the objects inside the bucket. You may remember that little peccadillo. And so here, you've got access control policies that either can be identity-based or they can be resource-based policies, because S3 is one of those rare services that will use resource-based policies, right? Now, by default, you have to undo the security, also known as block public access, in order to allow anybody access to your bucket, regardless of your identity policies. This became such a problem where people were inadvertently opening up their buckets to the world that Amazon has gotten really like notification heavy about this. For example, which of these buckets is public, right? Well, instantly notice the red exclamation point, right, on BAH admins. And as you get inside it, by the way, there continues to be these things that like, hey, by the way, this is publicly accessible. Hey, by the way, this is like, it just kind of like lets you know that you're making things publicly accessible. This is important because people keep sharing information out across the internet, not realizing they're making things publicly accessible. Notice, by the way, here that there is a resource-based policy. What is the one thing in there that is unique to a resource-based policy? What do you see in there that is unique to a resource-based policy?
Principal?
Principal.
Principal. That's exactly right. Principals exist only in a resource-based policy. You won't find them inside of a identity-based policy because the policy is attached to a principal for identity-based policy. So we don't need to define the principal because the policy is attached. With a resource-based policy, you have to say who can access this bucket. In this particular case, star means everybody. Notice, by the way, that 2919 is the only thing allowed to be public, which is kind of funny. This is the only resource people can access. Okay, so that's S3 and it's access control. Oh, I was going to show you this. So see this? This is the block public access settings. This is what they're referring to here. This is a setting underneath permissions for any bucket that you have to disable in order to even allow anybody to get to it. So think of it as a second firewall in front of your S3 bucket. Now, the other thing you can do is you can turn on versioning so that you'll never lose a file unless someone programmatically goes in and deletes all versions of a file. So what this means is that if someone changes a file, it's going to create a full copy of the old file and then write a new file. And so if you change a file 30 times, you're going to have 30 copies of a file. If you change a file 30 times and then delete it, you have 31 copies of the file. Because in order for you to delete a version file, you have to delete the delete marker and the 30 prior versions of the file that the system has. So just know that a delete marker, deleting a file, is just another version of a file. So versioning, by the way, is very useful if you want to protect from accidental deletion or, you know, for data retention. By the way, you can turn on locking if you want to, where you can lock an object where it can only be read. It's write once and read many times. So you can do that as well. Okay. So beyond versioning, beyond access control and other pieces, let's talk about storage classes. So I mentioned that there were 6 storage classes. And what's interesting is that technically that's true, although sometimes I think of intelligent tiering as kind of a meta class. But you've got standard S3, you've got standard infrequent access, you've got standard one zone infrequent access, and then you have these two. These two, by the way, are archival services, meaning you can't access the file directory directly. What you're doing is you're just backing it up into a vault. So the data is there, but you have to restore it before you can get it. So just know that Glacier and Glacier Deep Archive does not allow direct access to a file. You have put it into a vault or a backup at that point in time. So note that this is milliseconds to access for these first 4 storage classes. This is minutes or hours to access, and this is hours to access, meaning that the last 2 storage classes, the archival classes, are, again, archival services. So you can, by the way, create lifecycle rules that move a file from standard to IA to Glacier to, like, you can do, or delete it. You can create these lifecycle rules that allow you to automatically, based on age, move a file around. Now, if you don't want to come up with that because you don't know what your access patterns are, this is what intelligent tiering is for. Intelligent tiering uses machine learning to watch your files. And if they haven't been accessed in 30 days, it's going to move it over to standard one zone. If it hasn't been touched in 60 days or more, 90 days, it's going to move it to Glacier. And if it hasn't been touched longer than that, it's going to move it to Deep Archive. So intelligent tiering will automatically move your files around based on the access pattern. You can specify some minimum and maximum boundaries if you want, but intelligent tiering is like a machine learning based tier of storage that automatically moves things wherever they need to go. So this one gets used when you don't know your access patterns. Now remember, Glacier is archival storage, and there's Deep Archive and there's standard Glacier, right? All these, by the way, have 11 nines of durability, so they're all ridiculously durable. hard to lose your data. I think it takes like 100 years for them to lose one of your 10,000 files. Glacier, by the way, and Glacier Archive use the concepts of vaults and archives. They don't use buckets and prefixes. So they use basically a vault. Inside the vault is an archive, or in S3, that would actually be an object. It wouldn't be a prefix. And so vaults and buckets are synonymous for S3 and Glacier. When you stick something inside of a vault, just like you can with S3, you can lock it so that nobody can change it. You can do it for a period of time, right? Or you can do it indefinitely, which is scary. When you retrieve from Glacier, you can do an expedited retrieval, a standard retrieval, or a bulk retrieval. What this means is that you say, hey, like the security guy walks up to you and says, hey, I need the web server logs from last year. And you're like, when do you need them by? And they're like, I need them within 15 minutes. You're like, okay. That would be an expedited request. If you're like, hey, he's like, hey, can you get it to me by the end of the day? That would probably be a standard retrieval. If he's like, hey, I need files from last year, the year before, the year before, and the year before, when do you need that? You know, tomorrow, right? That would be a 12-hour turnaround. Give or take on the size of the files, right? This expedited one, by the way, you will get charged pennies to do. So if you do 1,000 of them, you're gonna pay some money. So just be aware of it. Expedited is really for urgent requests that all of a sudden have come up upon you, okay? Now, lifecycle policies allow you to move beyond retrieval and Glacier and all this other stuff around Glacier into general data tiering or data movement based on age. So this is a waterfall model where it's like, hey, it's 30 days old, move it here. It's 180 days old, move it over to Glacier Deep Archive, right? It's 365 days old, move it here. You can actually set up these lifecycle rules to take action based on objects inside of your buckets. So there's lots of options here to like make your data cheaper based on its access pattern. That's basically what this does for you. Now you can turn on encryption at rest. By the way, you can do this for hard drives for EBS as well. But you can also do this for S3 for object storage. So by default, Glacier encrypts everything, but you can actually turn on either using AWS managed keys by basically S3, KMS managed keys, or customer managed keys. If I remember correctly, Travelers uses customer managed keys for encryption, right? These are all server-side encryption options. So to be clear, these are not client-side encryption options. These are all server-side, which means 2 of them has Amazon managing the keys for you, right? And 1 of them has a customer managed key, which is the master key that encrypts all the data keys. Server side, sorry, KMS managed keys doesn't cost a little bit extra. I don't think that the SSE keys, the S3 managed keys, I don't think they cost extra. And then in addition to encryption and data classification and tiering with S3, you can also just replicate data. So you can actually set it so you can actually do cross-region replication. You can replicate within a region. You can replicate from one region to another region, right? So just know that the only exception really to this kind of replication is one zone. One zone in frequent access, by the way, is not like fully redundant because it's a single availability zone service. So if you put data in one zone, I'm sorry, just to be clear about that, it doesn't stop you from replicating it, but that's one you might want to replicate if you're not going to maintain a 3 availability zone subset, which is what standard does. One zone IA actually has the data could potentially is less available, not necessarily durable, but available because it's only in one availability zone. So you can use cross region or cross available AZ replication to replicate that if you want to. Objects stuck in S3 can send event notifications. So every time someone sticks a new file in, you could trigger Lambda, you could trigger SNS, you could trigger whatever, right? Just to mention this, once you get to Lambda, you can pretty much call anything else. CloudWatch events is kind of the same way. Once you get to Lambda, you pretty much can call anything else you want to. I actually ran a business based off of this back in 2014, 2015, a video business. And every time a user uploaded a file, it got transcoded into a bunch of different versions. And that was all Lambda based, because Lambda had just come out, I think, in 2014. So we were using it. You can also accelerate transfer acceleration. So those edge locations that we were talking about with CloudFront before, if you need to speed up the receiving of files from your users, you can use transfer acceleration, or you can use multi-part upload, or both, actually. And what that does is that instead of going all the way back to the source, if your users are in Japan, for example, and your server's in Virginia, it'll actually hit a server in Tokyo and then run over Amazon's high-speed backbone all the way back to Virginia. So it won't run across the internet, and it will be faster because there won't be any contention around traffic. Multi-part upload, by the way, allows you to parallel upload a file. I have sometimes found this confusing because this only really works if your bandwidth allows it. If you're already saturating your bandwidth, then splitting it into multiple parts isn't really going to help. But if you're not saturating your bandwidth, because let's say you're capped at 5 megs per transaction, then multi-part upload may make sense. By the way, when you upload different pieces, by the way, of a file, they are stored on S3, and once all the pieces hit 100%, Amazon assembles them and then puts them into S3. So if this takes weeks to run, because part 4, which is at 12%, hasn't gotten to 100%, Amazon's going to keep those other files in cache for you on S3 until you do reach 100%, which is actually pretty nice. And then there are things that you can do, like you can actually set access points, right? So what this does is this allows you, outside of speeding, acceleration, and transfer, it basically allows you to create access points for like reading and getting files. Access points are attached to buckets with a bucket policy. And what this does is that each access point has its own distinct permissions and network controls to access a particular bucket. So think of the access point has an alias to your bucket, but it has customizable permissions and actions to it. So for example, you might make it so that the sales team can only read the financial data. So all they can ever do is just like look at it, right? The accounting team and the finance teams, though, might have like change capabilities, but they might have different URLs that they access it with, because you want to make it easier for them to do that. Now, could you just go in and give the sales team read access versus giving the finance accounting team write access? Sure, you can do that. But this is just another way to solve that problem. This also, by the way, allows you to make S3 buckets private, right? So access points is another feature, is that you can then put these into your VPCs so that people can get to them privately. I personally have not found a lot of use cases to use access points, but someone at Amazon, some customer of Amazon must have needed it. I usually just modify the IAM policies to grant the access that I want to the objects that I want. But just know that you can create custom entry points into your S3 buckets. Okay. This is a relatively new feature called Object Lambda. What this does is this allows you, for example, to take an original object. So you could just retrieve it directly from S3. What you could also do is that you could actually make it so that if someone goes to retrieve something from your S3 bucket, you could have it run through a Lambda function and have it like filter things. Like it could filter data out, it could redact confidential information, it could like dynamically or automatically like resize images, for example, based on what browser or whatever the user's using. So this is a way to automatically trigger some kind of code action against files that you're pulling off of S3. This is relatively new, but it basically allows you to process data as it's being pulled off of S3. That's what it does. You can change it in some form or fashion. All right, other things to think about. S3 has a couple dimensions of cost, which is basically how much data are you storing? How much data are you pulling out of S3? So they charge you on a per gigabyte basis. And then any kind of like copies, posts, lists, like they charge you for reads and writes. Like what are the number of API calls you're making to your bucket? You do not have to pay if you want to transfer stuff in, and you don't have to pay if you're pulling from, say, CloudFront or EC2 in the same region. But be aware that you do pay for data that you pull out of S3. So API calls, data pulled out, and the size of the data are what you pay for in S3. Best practices is to make sure you have some lifecycle rules, right? Make sure that you've got encryption, replication, and versioning if you need that. Manage your permissions properly. And then you can use things like CloudWatch to kind of monitor and manage. You can also turn on S3 access logs if you want to get more data about who's accessing your S3 and what they're doing with it. So, and remember, S3's use cases, it's absolutely perfect when you need a large amount of files spread over with a diverse amount of content or just data that continually grows, and you need to keep it, but you want to keep some of it hot, and you don't need to put it inside of a database. Now, I say that S3 is a great staging platform for data that you're going to eventually put into a database, but may not need to do it like right then and there. Maybe it doesn't need to be real time, right? So like real-time data access is not what S3 is for. High performance data access is not what S3 is for. If you want data structured and retrievable or analyzed or use it for transactions, that's not what S3 is for. It is not a database. It is simply an object storage system. Okay. Any questions? All right. It seems like we might be good for a break. What do you think? Break is good? All right, it's 10:36. Why don't we come back at 10:51? I'll put a timer up, but let's come back in 15 minutes, okay? We'll see you in just a second. Welcome back, everybody. All right. Da, 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 da. Okay. Questions about anything related to storage, about object storage, block storage, file storage. No. Okay. All right. Question. All right, I have questions for you. If I can share questions, is it okay if I ask you questions? So, all right. So let's say I was like the penultimate lazy instructor, and I was like, and I said, you know what? I'm going to mount object storage inside my operating system. People do that all the time, right? And your answer would be, what would you say to me?
It's not possible.
Well, oddly enough, our people have written programs to mount S3 inside of a file system, but technically you'd be like, yeah, you're right. That's a bad idea, Michael. We don't want to do that. Don't mount S3 inside of your operating system. Good. Okay. If I said, you know what, I really want the fastest performing file system possible that I can possibly mount inside of my operating system, I'm going to use file storage. What would you say to that?
Don't do that.
What would you say, Alex? Say that again.
So don't do that.
Don't do that. Oh, okay, but why not? Like, what's wrong? I'm just going to mount an NFS server or a Windows server across the network onto my operating system. Are you saying there's a better, faster tier of storage that I could use inside AWS?
EBS.
Ah, EBS. You're right. You know what? What was I thinking? EBS is definitely the thing that I could use because that's faster because it's like direct attached, right? Okay. If I said, you know what? Whew, this people came to me, they asked for the fastest EBS volume that I could attach to my EC2 instance. And out of the 4 types, out of general purpose, provisioned IOPS, the streaming throughput one, and the archival one, I think the archival one is the fastest. And your response would be?
Nope.
Okay, so then which one is the fastest? Which is the fastest of the 4 volume types that I can mount from EBS onto an EC2 system? What's the fastest one?
The IOPS.
That's right. Provisioned IOPS is the fastest one. Good.
I don't know how you remember all the letters that go along with them. Like, you know, class-wise, you can remember if one is, you know, slow, one is fast, but I don't know how you remember all those letters and stuff that Amazon wants you to memorize.
Well, you know, do it for 10 years and it'll memorize. Just to say this though, honestly, after the first year of using it or 2, you just start picking it up, right? It's just exposure. That's all it is. It's not even like intentional practice. It's really just exposure. So after you kind of like live it off and on for like a couple of years, you're like, you'll get it. So, or you can be more intentional about it, which is, you know, what I recommend. And you can actually just, you know, memorize it and practice it. And eventually you'll just have it like the back of your hand, right? So it just depends on how you want to approach it. So it comes with time. But now if you put me into Google's arena and said, hey, what do they nickname their little drive? I couldn't do that, right? Because I have not worked with Google for more than 5 years. And I actually don't mess with it a lot because Google's not everybody's first choice on an enterprise. So not that it's not awesome. There's nothing wrong with it. Just not everybody's first choice. Okay. Okay, so a couple other questions. If we're messing with S3, because that's the technical term for engineering is messing, right? If we're messing with S3 and security comes up to me and says, look, does S3 have the option for us to lock a file so that it can like not be touched again, so it can be read-only? What would your answer be to that? Is that yes, you can, or no, go away?
Yes, you can.
Yeah, you can actually. What if a junior admin accidentally deletes a file and it's an important document that changes a lot and you want to make sure that they can't permanently delete the file? What would you turn on inside the S3 bucket? Perfect, Anastasia. That's correct. Versioning. So versioning, right, is what you would turn on. Good. If I had a friend who was like over in Russia and he has like this awesome crypto wallet that he wanted to share with me, and I wanted him to put it on my S3 bucket so I can then decode it and do all this stuff with it. And I wanted to speed up his S3 transfer. What two things could I turn on with S3 or have him turn on with S3 in order to make sure that his transfer from Russia to my server in Brazil went faster? What would I turn on?
CloudFront?
Say that again, Alex.
Was it CloudFront?
Well, CloudFront is definitely like the edge servers that CloudFront uses are used in that. But what are the two features in S3 that I would turn on? So for example, if I wanted to parallelize, I wanted to actually break his transfer into multiple parts. What is the name of that S3 feature? Does anybody remember?
The partitioning.
God, I love that you're partitioning. Yeah, from the EC2 thing. How about this?
Yeah.
Multi-part upload. So
Multi-part.
good. So that's parallelization. So you partition it out into multiple parts. That's accurate. All right. And the last one is this one, transfer acceleration, right? This allows you to speed the transfer over Amazon's high-speed backbone instead of running stuff over the internet, right? Good. All right. There's enough quizzing for now. Anybody have any questions about anything we just talked about? Okay, let's talk about the next piece. Okay, so this is where we actually start getting into shared file systems, right? This is block storage, but it's run over the network. So we call it file storage because the drive letters that mount inside Windows, or if you take a MacBook or Linux box and you mount a remote server and it looks like a local file system, that's a file server. Different than object storage because you don't ever really mount object storage inside your system. So what if I have a fleet of 1,000 web servers and they're all using the same HTML and I want to mount that HTML directory across all 1,000 of those servers, right? Well, that's where a shared file system like this comes in. Notice in the lower right-hand side, it says very clearly that Amazon EFS and FSX are perfect for this task of shared file systems. This is what you use when you want to mount the same system across all these boxes. And by the way, some of them are multi-OS, although in general, Windows needs a few kicks to mount NFS, and Linux needs a few kicks in order to mount SMB, CIFS, or Windows file sharing. So just know there's little extra steps there for the opposite operating systems. Now, EFS, so you may remember earlier, Alex and I were talking about these load balancers that then stick network cards inside these like VPCs or subnets, right? EFS does something remarkably similar. You create a mount point for EFS and say, and you tell it how fast you want it to be and how much, space you want to use, although you can grow that easily. And then what happens is it puts what's called a mount target inside each of your networks or VPCs or availability zones inside the region. This cannot span regions, to be very clear. This cannot span regions. Okay. So inside of a region, EFS can actually stick what's called a mount target in every place that you want to stick one. And then what happens is that this is NFS actually version 4.1. Why the .1? I don't know. And so what happens here is that now the EC2 virtual machines that are inside these availability zone subnets can mount this file system into their operating system. So now when you're poking around, it looks like it's part of the operating system. That's it. So just know that this allows you to mount everything against a large fleet of servers using NFS. Now, the next one, oh, sorry, hold on. Let's talk about the use cases here. So EFS, by the way, has 4 nines of availability, right? but it uses S3 as its backend for replication. So it matches S3's durability, which is 11 nines. By the way, that does show up on the exam. You can do auto scaled throughput. So if you don't know how fast you need it to be, you can just allow it to use whatever you ask for. Be careful with that. You get some rogue agent in there who starts asking for 20 gigabytes a second. You might be paying a lot for your EFS. But this is like a mounted file system. Now, by the way, EFS can replicate not only within a particular region, but now you can take backup snapshots and copy and restore those snapshots over to other regions. So you can actually make it, I wouldn't say real time, but region to region snapshots are easy to do with EFS. Interesting. Bear with me just one second. My system's having a little problem here. All right, so EFS, by the way, automatically replicates data when and across availability zones. So you don't have to worry about redundancy. Like if an availability zone goes down, EFS is still available, right? When you mount, by the way, a file system using its DNS name instead of trying to mount by availability zone, it automatically does failover. So you don't have to worry about the loss of a file system. Basically what this does is if you use the DNS name instead of mounting it by like an IP address as an example, what will happen is that if that IP address goes away, the DNS name will be updated and pointed to another mount target. So your system will recover within milliseconds to seconds instead of taking an outage. So no re-architecting, automatically grows and shrinks both in speed and in storage. So it's a great option to have. Now FSX, so this is a weird thing. EFS came out first and it's built for Linux and NFS. Doesn't mean Windows can't mount it, but it's built for Linux and NFS. Then some other team at Amazon came out with FSX for Windows File Server, but they actually have 3 flavors of their FSX service, which is different from EFS, which just has 1 flavor, which is the Linux flavor. So FSX has Windows File Server. It has FSX for Lustre, which we talked about earlier in the high performance computing section. It also has FSX for ONTAP, which is the NetApp file system. So if you're familiar with storage, because you're a storage engineer, great. If you have no idea what I'm talking about, then just remember that I said FSX for ONTAP and let's just move on because it's not going to be super relevant, frankly. But the FSX for Windows File Server is incredibly relevant because this allows you to natively present, just like EFS does, a file system to Windows boxes. So it's got a wide range of features to it. Now, FSX for Lustre is that high performance computing system I talked about before. It's really built for Linux. I think Windows can mount it if you put a driver on there, but it's really built for Linux also. So it's a little strange, frankly. The same team is doing Windows and Linux, and there's another team doing Linux. And anyway, just know there's 4 services for shared file systems inside of AWS. There, by the way, it does integrate with Microsoft Active Directory. So if you're kind of like, hi, I'd like to integrate this in and have my same file permissions that my Active Directory uses, manage my file permissions for this file share, guess what? And then it supports DFS and, oh God, there's so many other things that it supports off the top of my head. Active Directory integration, NTFS, DFS, SMB protocol. So I think that's pretty accurate. Lustre is that high performance file system I was talking about before, SSD based. This is really useful for when you have ENAs, ENIs, ENFs. We talked about those earlier. Elastic network adapters, elastic network fabrics, right? These are faster HPC networking devices. This is where you want to use Lustre because if you're going to get to 400 gigabytes a second across the network, you're going to need a file system that's going to handle that. So Lustre, by the way, will actually mount S3 as part of the file system. So this is some of the craziness that Lustre is an open source product and they will actually mount through S3 as part of their file system, but only so you can put files there. You don't really process files there. So it's just really used like the output of processing. So you can just like stick stuff out there. It just makes it easier than I guess you were having to run S3 commands. I got to tell you, performance wise, that is fraught with peril. If you haven't heard that term in a while, fraught with peril to try to use S3 as a file system and have it be performant. Okay. Okay, so that's the file system share that we just talked about. What about data migration tools, right? There was a whole list of them, including some security tools that we looked at the beginning of everything. So what data tools do we have if we have like data migrations? Well, don't get me wrong, Amazon in usual form or fashion has some really sane offerings, and then they've got some ridiculous offerings. And I mean ridiculous just because in terms of like size, like who's actually going to use that? But oddly enough, there are customers who actually need it. So let's talk about it. First of all, you got to know they have offline and online options, and they got a bunch of tools for online. They only have one family of tools that's really good for offline. This is like the snowball, and like snow cone, snowball edge, like snowmobile. I can't even, it's just hilarious. I laughed because I was there when they drove the truck onto the floor. I think it was 2016 at reInvent. And they drove this truck out into the middle of this Las Vegas stage. And then the truck showed up later inside the vendor floor. We're like, how did they get this truck around? It's like Optimus Prime, just like running around and transforming. Bottom line is that these devices are used when you want to transfer data offline. You put data in these boxes, it all gets in there, and then you ship it back to Amazon. Either you drive it, which is what the snowmobile does, or with the edge of the snow cone, you just send it back, and the data will get processed by Amazon, and then it's stuck inside your S3 buckets. Now, there's a little bit of a difference here, is that the Snowball Edge is actually a computing device, as is the snow cone. So snow cone and Snowball are actually computers that you can actually use as like IoT edge devices. Some of them are compute optimized, some of them are storage optimized. But there's a whole family of portable computers that are remotely managed. They are managed at a distance by AWS that you can use as independent portable computers using your same APIs and whatnot that you use with AWS. The snowmobile, by the way, comes into your data center near it. You run some cables to it. It has its own independent power and cooling. And then when you're done with the data cables, it goes with an escort back to AWS. You can transfer 100 petabytes per snowmobile truck. If you were to transfer that across, even 100 gigabit connection, it would take you a while to get that into AWS. This would allow you to do it within 10 days. So just something to keep in mind. Oh, the process, by the way, is you go to the console, you ask for the device comes to you, you upload data to the device, you send it back to Amazon, they stick it on your S3 bucket, right? So just know that this is a send, dump, retrieve action, okay?
Do you know what type of customers actually use that?
Actually, I've used the snow cones and the snowball edges, both of those. I've never used the snowmobile. I think the stories I heard was like in Florida and Louisiana when there were floods, and data was coming and they had to get out of the data center because for whatever reason there was something faulty. There were customers who actually used snowmobiles to get their data out of the data center, their backups and their archive, like their precious data, as quickly as possible. But
okay.
Yeah, for snowball edges and snow cones, those get used all the time. I've had small companies use that because they had like for example, a 70 terabyte database, which if I remember correctly, the snow cone can go up to like 73 terabytes. It says 80, but it's 73 usable. We would dump the database into that, and then we shipped that up to AWS because we didn't want to wait for 70 terabytes to transfer because,
Right.
Yeah. And don't get me wrong, the next tool we're about to talk about, the data migration tool or the database migration service, could actually replicate that data, but it was going to take 6 weeks for it to replicate up based on our current bandwidth projections. So as far as the computing and the storage, like edge devices that are here, other places that use them are factories, airplanes, connected buildings, like for building maintenance and stuff like that. So there are actually specialized use cases that are mainly edge cases, like not core data center cases, but where you're out like in a building or a factory or a steel mill, or you're on an airplane, where these devices can come in handy. Was that Aaron that was asking?
Yes.
Okay, good. Just trying to recognize voices. Let's see, snowball process. Okay, data sync. So data sync is different from other specialized migration services like the database migration service or the server migration service or Amazon has a lot of migration services, some of which are really cool, some of which are just kind of like this guy, which are just kind of like simple data transfer agents. That's all they really do. I'm not diminishing it. I'm just saying like the database migration service is really just a specialized database transfer service. Data sync is a generalist. So like data sync, for example, is mainly used to sync shared file systems like NFS or Windows file shares. And what it does is it will do it encrypted, and then you can dump it either onto S3 or onto EFS or FSX, right? So this agent just gets installed on the operating system that you want to have leverage this, and then it just pulls and syncs the data. This is not a fast process depending on your bandwidth. So again, if you have time and you just want to maintain a continual sync, this might make sense. If you need to do it faster, then something like this would probably make more sense. It all depends on the size of the data. Everything changes when we go up in scale. So just something to keep in mind. So the data sync agent runs locally and this does the transfer for you. By the way, this is all managed from the console. So once the agent can talk to AWS, you can actually just manage it from the console. And then there's a storage gateway, which the storage gateway solution is basically, this is a virtual machine. So unlike this agented data sync service or these hardware devices, this storage gateway is actually a virtual machine. And they've had this for like 10 years. This is crazy. And I've used this a couple of times. Basically, it can act as 3 different things once it's a virtual machine on your network. If it's on your network, it can either act as a file gateway, like a file server, like an NFS server, right? Or it can act, oh, they're not showing it. Oh, actually, you know what? They are showing it. So just to emphasize this, it can act as a file server, either Windows or Linux, right? I got that backwards, but you know what I mean. It can act as a volume server where it actually shares volumes using what's called an iSCSI protocol. Man, for those of you who've been around for a while, you've probably heard SCSI before. iSCSI is the network version of SCSI. And then it can act as a virtual tape library. This little appliance is actually pretty cool. I mean, the fact that you can put it into a file server mode, a volume mode, or a tape mode, and then everything that you copy to it is either kept local in your data center, and then a backup copy is put in AWS, or it only caches recently accessed files locally and it puts everything in AWS. So it really depends on where you want to home your data. Do you want it to live on storage that's inside your data center? Or do you want it to live solely on AWS and frequently accessed files are cached forward? So just know this little appliance, which again has been out for a long time, is really adaptable and useful if you need to have some kind of storage mechanism to either expand your storage capabilities or just replicate your storage over to AWS. So pretty cool. Okay. We're on to a knowledge check. Let's test your knowledge. Let's get rid of Michael's little drawings first. All right. Which of the following is a petabyte scale data transfer solution that Michael referred to as Optimus Prime? Come on, that's a useless bit of trivia. Good, yeah, so the snowmobile, right? By the way, bonus points, where none of the points are real. How many petabytes can that system handle? Can the truck handle? No? 100 petabytes. There we go, Patrick. Good. Yeah, 100 petabytes. 100 petabytes of data. Good. You heard me refer that the snow cone and I'm going to say the snowball, not the snow cone. The snowball edge typically comes in this size. What's the size? How many terabytes can the Snowball Edge usually handle if it's not storage optimized, just the standard one? I said it out loud. Because I made a distinction between what they advertise and what's actually usable in the device. I said, oh, they say it's 80, but I said it's actually, yeah, 73 usable. Yeah, so just know that you're gonna get about 70, 73, right, usable space, because it says 80 terabytes, but the usable is actually less than that. Good. Okay. Oh my gosh, it says the Snowball Edge is a petabyte scale service. Is that accurate? It is accurate. I'm sorry. That could be a petabyte scale service, but that's not the way I understand it. I think the answer here is wrong, actually, because we just clearly saw that the Snowmobile is 100 petabytes.
Aren't they both though?
Well, what is the upper edge for Snowball Edge? Let's go take a look. Maybe Michael Forrester needs to update his information. Let's go take a look. All right, so if we're looking for the Snowball Edge capacity, see, that's the thing that's confusing because it says 80 terabytes, right? This is the Snowball Edge. This is the storage optimized version, right? So let's go take a look at it. Why would they say that was a petabyte? Maybe we missed something. So I see 80 terabytes of memory. I see, yeah, 42 terabytes of usable hard drive capacity, 80 terabytes of hard drive capacity. Yeah, so I don't know why they would say that. But Aaron, you mentioned it for a reason. Did you see somewhere else that there was a larger storage size for the Snowball?
No, in the notes of slide 47, it just says that it's a petabyte scale data transport option. And then for AWS Snowmobile, it says up to 100 petabytes.
Right, so that's confusing because the max size for that is 80 terabytes. So why would they say that? And I've heard that from them before, just to say this, but it doesn't go above 80 terabytes, even for the largest one. I'm going to take a note. I will talk to AWS and find out. Technically, though, I don't think that's accurate. So, but let's assume that we're wrong. But we know for certain the Snowmobile can handle a petabyte, right? Okay. Which Amazon S3 feature can force an action to occur after an event takes place within a bucket? In other words, what can trigger another service? Not change the data, but what can trigger another service? Now, I just want to say this is that technically it's event notification, but some of you are thinking of Lambda actions because we talked about Lambda actions, but it doesn't say Lambda actions. It just says Lambda, right? But you were thinking about Lambda actions, which warms my heart somewhere. But just to mention this, Lambda actions only changes data when you retrieve it from S3. It doesn't actually trigger another service. So it's not an event trigger, which is exactly what event notification is, right? It's an event trigger. So it will trigger an action to occur after an event. Now, if it said, if you wanted to force a change in data or a filter against data after someone pulls it, that would be Lambda actions, just to make that distinction. But otherwise, it's S3 event notification. Okay. Okay, we've got two Linux applications in different availability zones in the same VPC, obviously, that must share a common file system. What solution would you choose? And actually, I'm just going to say this. They're in two different availability zones. That's an important point. Which one of these is designed for Linux? Good. So D is designed for Linux. B is designed for Windows. C, by the way, is also designed for Linux, but it's for high performance computing. And I think it only runs in one availability zone, if I remember correctly. I actually haven't run Lustre in AWS, But if I remember correctly from the documentation, it only runs in one availability zone. And storage gateway is a data center thing. So it is actually D in this case. Good. Okay. This one is a little funky because we didn't really get into this. But what are the 3 protocols that the storage gateway virtual appliance will actually support in your data center? One of them I made mention of. I was like, man, if you know this one, you've been around for a while. There were 3. Patrick, I feel like you're messing with me a little bit, just a little bit. You may not be messing with me, but I feel like you're messing with me. Because I was making fun of FTP, right? Earlier, I was like, hey, I still have access to an FTP server, right? Which you would think that FTP servers would have been retired, but no, they're still around. All right, so let's check this out. So what protocols would I use if I was a file server? So someone answer this for me. If I was a Linux file server, what protocol would I be using? Someone type it out for me. Or say it. No, SMB is for Windows. So that you answered my other question, Arpan. What's the Windows protocol? SMB would be it. So Alex, NFS is the Linux one. So that answers 2 of our questions, is that SMB and NFS are file server protocols. We know that the storage gateway can be a file server. So those are 2 of our protocols. Now, I mentioned that it can also present hard drives or volumes, and it can present tapes. It uses the same protocol to present both of those. And I kind of was like making fun of it a little bit, right? Which is iSCSI. SCSI, it stands for Small Systems Interconnect. Oh man, Small Computer Systems Interconnect. That's what SCSI stands for. It's an old protocol back from the 90s and early 2000s. And the iSCSI version is basically the internet enabled version, which means it runs over the network. So iSCSI, FTP, and NFS are our answers. Sorry, did I say FTP? I was joking. iSCSI, SMB, and NFS are our options. FTP, by the way, is the same as S3. That's a remote system, right? FCOE and FC are fiber channel and fiber channel over Ethernet. A virtual appliance can't do that. Virtual appliance, that would require physical access. Okay. Any questions about module 5 and all the kicking around we just did around storage? Okay. So our next module is actually going to be module 6. It's going to be about databases. But I know this is kind of a weird ask, but my computer is doing something really weird and I need about 5 minutes. So can everybody take a 5-minute break and come back at 11:30? I just need to kick something around for a second because it's doing something weird on my screen. So give me just 5 minutes. So everybody take a 5-minute break. That's okay. All right, excellent. I won't put up a timer this time because I'm gonna be messing with my computer. So 5 minutes, we'll be back at 11:30. Okay. Welcome back, everybody. Give me a thumbs up and reactions just to make sure I know you're here. Oh, wait, good. We've got a quorum. All right. So we're switching off of storage and we're talking about database services. Now, I'm just going to forewarn you, if you're not into databases, much like a lot of this is just going to be an overwhelming amount of information with very little to no context. Just know, here's the general rule of thumb about AWS databases. If there's an open source version of it and it's popular, Amazon probably has it. If you're looking for Postgres, MySQL, MariaDB, they've got it, or MariaDB. You want Neo4j, which is a graph database, they got it. You want MongoDB, they've got it. You want Cassandra, they've got it. You want Kafka, they've got it. You want Elasticsearch, they've got it. You want Solar, they've got it. I know that sounds weird. They also have a bunch of services, by the way, that have no open source analogs, like DynamoDB, right? And don't let me like trivialize what Amazon's doing. For example, if you've ever used Aurora, which is their like version of RDBMS, Postgres and MySQL in particular, it's a crazy advanced beast. They have a serverless version of it. Version 2, super awesome. Could not sing its praises enough, right? Awesome improvement among a 30 or 40-year-old technology. But that's basically what we're going to talk about. Is we're going to talk about these database services. Now, here's a big question for you. If you run your databases on a virtual machine, which of these are you responsible for? And think of server maintenance as hardware maintenance, by the way. Which of these are you responsible for if you run these inside of a virtual machine? Yeah, so if server maintenance is hardware maintenance, you're not responsible for hardware maintenance, but you're pretty much responsible for database backups, OS patching, and scaling. That's all on you, right? Not necessarily the most fun thing we could be doing with our time, right? Especially when we already are all pretty overloaded, right? Now, just to make sure this is super clear, Amazon wants you to give them as much operational offloading as possible. So if you're going to roll your own databases in your own virtual machines, you're going to take a lot of this responsibility. If you let Amazon do it, guess what? There's not as much responsibility. So let's talk about database services. We're actually going to do the lab after lunch because it's already 11:30. So we'll do it pretty much right as we get back. So here's the thought that we need to process. We have a new database services team. There are a lot more databases in production than we expected. We want to support everything we have, which includes Oracle and like MSQL Server, and we're using Memcached, which is a caching engine. So what database solutions does AWS have? What are our options for managed services? Because we have way too many databases to manage. How do we do database caching? Who can simplify migration? What does that look like? So what are the database solutions? What are the relational and non-relational database service offerings? How do we migrate to cloud? How do I cache my databases? And what about data warehousing? So Amazon's got an answer for all of this. So notice our database architecture in the upper left is DynamoDB. In the lower right, we have a caching system and we have a database system. That's what we're focused on now. So let's talk about at a high level, the various database services. So I got to tell you, there was a certain point in time where it wasn't cost effective to use managed databases on AWS. That changed about, let's say like 6 or 7 years ago. And they are way more efficient at it than, I'll be frank, than any of us are. So here's the whole plethora of services, but we're only going to talk about 5 of these. We're not going to talk about MongoDB, and we're not going to talk about Cassandra, and we're not going to talk about Neptune, which is Neo4j. We're not going to talk about the time DB, the time stream. We're only going to talk about these 5. That's it. Before we do that, let me just throw this out there. SQL-based databases are known as relational database management systems. These are relational databases. The data is structured, and we've been using these for 40 years. Non-relational databases didn't start showing up until the early 2000s, And they are more interested in data as a blob of data instead of like having the data be indexed in relation to each other and in tables that are queryable. And they are a little less acidic on the consistency side of things, just a little less than relational databases, which are very consistent typically, but at the cost of performance. So relational data has this kind of format where there's like tables and there's links between patient ID versus hospital ID versus, there's structured sets of data that have a relational to them. This is why a structured query language is necessary, because you are talking to the structure or the schema of the data. This is a little different than a NoSQL system, in this case, a key value system, which basically says, hey, I want you to retrieve the gamer tag and then just give me everything they've got. Now, don't get me wrong. You can server side and client side filter those attributes data to only get the attributes you want. But you're not going to do a targeted specific query using a targeted specific language. You're going to basically use whatever language is appropriate for the key value store to retrieve the attributes you're looking for. Data is structured here based on keys that retrieve values. Over here, you can actually ask for a specific column, row, or thing of patient ID, which is exactly what you could do over here. The difference here is that this data is structured, so you're gonna have to pull from a bunch of different sources. Over here, the data is not schemaed. It's not structured like that. So you're just gonna pull it in one big blob and then filter it as you see fit. Now, in both cases, data is resilient to failure, but this is going to horizontally scale for the most part. And this on a read level will horizontally scale, but on a write level, it has to vertically scale. Snowflake is probably an example of a database system that's probably shifting that to a certain degree, which is kind of a hybrid. But this is in general how most relational databases versus NoSQL databases function. Now, when you choose a data store, the real question is how many transactions per second do I need to surface? And what's the data that's being retrieved? What about durability, availability, consistency? How does that get approached? And do I need to store simple data structures, large data objects, complex data structures, or both, right? Or all three, actually, because I said three. So you want to choose your like Oracles, your MS SQLs, your MySQLs, your Postgres's when you need a strict schema. You need a strict structure that's not flexible, and you don't need extreme write capacity. It says extreme read capacity. You can get pretty good read capacity off of using read replicas with a database. If consistency and like transactionalness is like kind of like more of what you need, then a relational database is going to be more important for you. If you want to scale horizontally and you want to go fast, oh God, that sounds like Ricky Bobby. You want to go fast? I want to go fast. Then non-relational databases are probably going to be your best thing to use. Economically, a NoSQL database will typically perform faster for the same dollar than a relational database. Typically, there are obviously exceptions to that general statement. So just know, if you need a relational database, you're going to use a different set of services than if you need a non-relational database in AWS or really anywhere. This is not an AWS specific concept. Now, past that generalization, the first question is, well, do you need an SQL? Do you need a structured database? Do you need a relational database? Well, there's really only one service, and that's RDS. Now, RDS has a subflavor called Aurora, which is a little different than the other flavors, but the rest of them, excuse me, are all open source analogs. This is, well, open source analogs. Oracle and MS SQL are not open source, obviously, but MySQL, MariaDB, Postgres, those are all open source analogs. Aurora, just for giggles, Aurora is a cloud-enabled, cloud-native version written by Amazon of Postgres and MySQL. So don't let Aurora fool you. It's not a separate product. It's a subproduct of RDS. It's not found anywhere else but in the RDS console. And it is Postgres and MySQL compliant, okay? Now here's a simple application stack. You got a load balancer in front of 2 EC2 instances talking to a backend database, and the snapshots are going into S3. This could be a multi-AZ deployment, except the database is in one availability zone. But here's the cool thing. With a checkbox, you can make the database secondary. In other words, you can have a primary database and a secondary database in 2 availability zones. If one fails, the DNS name is automatically changed and the boxes automatically fail over to the other system. So the primary fails, the secondary is promoted to the primary, and a new standby is initiated if necessary, or if the old one recovers, it just reconnects it. This is a checkbox, by the way, inside RDS. Check, I want multi-AZ. That's it. And it's going to ask you which 2 availability zones you want to span across, but that's it. That's done, right? You can also add read replicas, which that's why I mentioned before the caveat of like, well, you know, relational databases can't actually scale decently with reads, because I think you can add up like 15 or 16 read replicas to, like, for an example, an Aurora instance. This is asynchronous replication, by the way. So this guy is synchronous replication. So this is real-time replication. So when you're setting up a primary and a secondary, it's real-time replication. If you write to the primary, it automatically writes to the secondary immediately. With a read replica, it's asynchronous replication, which means there can be some lag, because the primary can queue up writes to the reads, and the reads can have, and you can look at replication lag to see, but like the reads can be out of sync. Do they get heavily out of sync? It depends on where you put them, but no, typically not. Usually, like, we're talking about like seconds or milliseconds. You can't put your read replicas, by the way, in other regions of the world. So while a multi-AZ deployment has to be within the same region, a read replica could be on the other side of the world. So you can actually put a read replica over in Tokyo while your primary is in Virginia. Note that that read replica obviously is read only. So, by the way, you can break the replication with a read replica and promote it to its own standalone database. So, which is pretty cool. It's a great way to spawn production databases in other locations. You can encrypt the data, by the way, by just turning on the KMS encryption. That's available for all the engines, so that's easy to do. There is that Aurora subset that I was talking about. So Aurora, by the way, is a subset of RDS, and it's only for MySQL and Postgres compatible databases. Here's something to know. If you take the exact same workload and the exact same database, and you stick it into MySQL, and then you stick it into Aurora MySQL, the Aurora MySQL database is going to be like 3 to 5 times faster than the RDS MySQL database. Amazon has done something to Aurora with the storage that makes it faster than standard MySQL and standard Postgres. So the Aurora version of those products is 3 to 5 times faster than the standard open source versions of those products. So they've peeled back some of that, but they really haven't like said what the secret sauce is. But just know that Aurora, just out of the box, is faster than its open source analogs. So other thing to note, by the way, is that Aurora has a serverless version where you only pay when a query is run and you pay for the storage of the data. That's it. Otherwise, RDS uses EC2 virtual machines that you can't log into, has the underlying unit of capacity, but Aurora doesn't do that. Aurora has a serverless version. So you can run Aurora in server mode, or you can run Aurora in serverless mode. All of the other database engines that are listed here all require servers underneath them to function. But Aurora has a serverless mode as well, just FYI. Now, you run database clusters with Aurora, which apparently it makes 6 copies of your data, and you can add up to 6 replicas, if I remember correctly, primary replicas to your Aurora database cluster. So you can actually do clustering with Aurora with MySQL and Postgres that you can't do with the other ones. Oh, I'm sorry, it's 15 replicas. It's not 6 replicas. Aurora maintains, you can see 2 copies each and 3 availability zones of your data. So just know that there's a lot of redundancy here. I mentioned serverless before. Starts up on demand and shuts down when it's not in use, scales up and down automatically, no impact when scaling. Version 1 of this was horrible. Version 2 of this is awesome, which it got released like, I want to say like 6 to 8 months ago. So you don't have to manage any database capacity here. It just handles it. You can set mins and maxes, by the way. Okay. So this is basically your RDS section. That was all relational database. Okay. Questions?
Why would we not use Aurora? Like what is it more expensive than its open source counterpart? I'm just wondering why you would just choose one over the other. Let's say you wanted to do MySQL.
So one reason is that while Aurora is MySQL and Postgres compatible, it's not 100% compatibility. So some of the plugins don't work in Aurora because Amazon won't allow unsecure plugins into their ecosystem. So that might be a reason. The other reason though is just lack of familiarity. People are more comfortable with the tools they're familiar with. Like we're all like that, right? We covet what we see every day. We are familiar with what we know. So that tends to be what we go after. Otherwise, I highly recommend that teams actually, if they're using MySQL, just go look at the Aurora version. That's the main reason, Patrick. And just to say this, the Aurora version, both just the plain Aurora version, but the serverless in particular, is going to be cheaper than running like MySQL on top of an RDS EC2 instance. So usually it's just a perception problem. It's not an actual fact problem, but as we stated before, it's always in the details. If you need a plugin that isn't available, that the AWS won't allow, then you probably need to run standard RDS or even your own EC2 instance with MySQL on it. But those are the main reasons, is either compatibility or just lack of familiarity.
And the serverless option really has to start up the database on each query. Is that what I'm understanding?
Yeah, but it's milliseconds.
So every request is going to incur extra time to start the database up and shut it down.
Nope, just the first request. So what will happen is that when you first hit it, you'll incur a little millisecond charge as it spins up the container that's running the system, just the interface, because the data's there. All they're doing is spinning up the SQL engine, right? After that first request, that container will actually stay and hang out there, listening for other requests for a period of time. So it's kind of misleading. It doesn't actually run it on a per transaction basis. It runs it when the first transaction hits, there's a little bit of a cost, but every subsequent transaction misses that like 10 millisecond, 20 millisecond startup time. So I know it kind of blows the mind a little bit.
Yeah, I'm thinking if it's that small and it does hang around for a while, then the serverless really becomes a real server for that amount of time until there's, I guess, a delay of, I don't know, a few minutes or whatever set, and then it shuts back down,
right,
wait there for, I guess, the next. So it's not really serverless. It's server full for a certain amount of time.
Yeah, but that's true. That's true for all the serverless services, right? All of them have servers, right? We just don't see them. I usually say that serverless is hidden servers. You just don't manage them. Because the Lambda functions, for example, also run in containers, right? That start in milliseconds. So yeah, it's the same consideration.
Yeah, but Lambda doesn't have the server option, right? It's just Lambda.
That's right. Exactly. They didn't offer a server option.
It's meant to confuse people, I think.
That, you
Like, all
know,
this- that's all this stuff.
if you really want to be entertained, all of you, you should sign up for Last Week in AWS. It's a gentleman named Corey Quinn who runs a billing company that just works on AWS. It's called the Duck Bill Consulting Group. He writes one of the snarkiest and most informative newsletters / blogs on AWS that you'll ever see. It's a great way to stay up to date about what AWS is doing. It's also very entertaining. He makes fun of them, Alex, all the time for their horrible naming and horrible marketing. He actually declares himself the unofficial like head of marketing for AWS because they haven't had one until recently. So, and they didn't have one for 10 years. So if you ever want to be thoroughly entertained, but also informed, Corey Quinn's a great gentleman to get hooked into.
As long as it doesn't confuse further.
No, he actually usually clarifies, usually by making fun of it in a way that you're like, oh, that's what that means. He's like, yeah, that's what that means. So, all right. Good discussion. Okay, so this is one of the services that's not an open source analog, but I say that there was a paper written about this in 2001 well before this service came out. And there's actually an open source company called RIAC, R-I-A-K, that publishes an open source version of DynamoDB. Doesn't use the same APIs or whatnot, but it's the same concept. It's a Dynamo based system. Now, this is a NoSQL managed database. So if we look at this application architecture, we got a load balancer in front of some EC2 instances talking to a NoSQL database, DynamoDB. That's it. This is really a serverless, like this is highly managed. You can't even see the servers here. At least with RDS, you can see that they started a server. You can't even see the back end for this. So DynamoDB, by the way, what is it they did the other day? Was it 10 trillion transactions an hour? God, it was something crazy. For Amazon Prime Day, DynamoDB was the backend database, and I want to say it was handling 10 trillion transactions like an hour or something like that, it was just ridiculous. And they were publishing like this paper about it and all this other stuff. This is a NoSQL database where, like, for example, the user ID would be the primary key. Everything else would be data, right? So that's all this is. This is just a NoSQL data store. It just stores collections of data. That's it. So in this case, this first use case, what's happening here is that we've got the web store, we got a shopping cart, we got order processing. Here's another use case. Well, in this particular case, DynamoDB can actually host the shopping cart information. So over here, it's hosting a leaderboard. Over here, it's hosting the shopping cart. DynamoDB, by the way, can also do session data. So if you've got a bunch of web servers on the front end and you want to maintain session state for users, you can store your session state inside of DynamoDB. Now, you could also use a caching database for that, but DynamoDB is a great use case for that as well. Here's a table. And in this case, they don't have a primary key alone or partition key. They have a sort key as well. These used to be called range and hash keys, right? But partition keys and sort keys can be put together to make a very unique primary key. I'm trying to think of, like, Tom Hanks was Chuck Nolan. What movie was that? I'm gonna have to look that up now. Anyway, regardless, what happens here is that this key is what you actually query to retrieve the attributes of year, genre, height, etc. Notice that there's some gaps here. Ah, thank you, Patrick. Castaway. That was going to drive me crazy, actually. So just know there's some gaps here. NoSQL wouldn't let you do that. You have to have at least a null value in there, right? You don't even have to have the attribute defined on a per row basis. This is what NoSQL does, by the way. Not every single field has to even exist in a NoSQL database. The attributes can be super variable, right? So this is how DynamoDB, because tables are the basic unit of deployment with DynamoDB. tables are what get capacity, like read and write capacity. So if you want something to have 5,000 transactions a second on read, you actually assign that to the table, and the table gets the capacity. So you can have multiple tables all with their own independent capacity, which is how DynamoDB manages the whole thing. Now you can turn on auto scaling, so you can have it automatically scale up and down as you see fit. So that way you don't have to worry about wasting or over provisioning or any of that stuff. Amazon will handle that for you. So in other words, if you ask for 100 transaction reads per second, it'll give you 100 reads. If you ask for 1,000, it'll give you 1,000, but it'll go back to 0 and do nothing if you haven't asked for anything. Now, here's the funny thing. If you do on demand, that's where you basically have no limit on your capacity ask. So just to say this, for unpredictable workloads, they do recommend that you use on demand. If you use provisioned, you're basically saying, look, I'm going to pay at a minimum for 5 reads per second and for a maximum of 5,000. If you try to go above 5,000, DynamoDB will send a throttle notice and say, hey, you're capped at 5,000, so you can't go any further. If you're in the on-demand mode of DynamoDB, you'll just go wherever you need to as far as capacity goes. You can also set consistency options, because one thing you need to know is that since this is a NoSQL database, by default, it is eventually consistent. Meaning that if you're just made a write and then you do a read right after it, you might actually hit a node that hasn't received the replicated data yet. And so if you have $100 in the bank and you just withdrew 50 and you say, hey, check my balance, you could get back a number that says you have $100 in the bank, even though you just withdrew 50. If it's right afterwards. So it's not really great for that level of consistency. In order to enforce that level of consistency, you can do a strongly consistent read, right? Which says, hey, I need you to talk to every single copy of this data and make sure they all say the same thing. If they don't, right, give me the latest changed data, right? So strongly consistent enforces consistency. Eventually consistent is a little loose with consistency. You might say that's horrifying. Well, if it's a recommender or, you know, something that isn't like competitive or legally or ethically like required, then eventual consistency might be fine, right? Now, in addition to governing consistency, you can also globally replicate data the world over using DynamoDB tables, which is really cool and can be a pain as well. Another reason I say that is that, again, this is eventual consistency. So again, if you're looking for real-time enforced consistency of data, this may not be your option, but just know that you can create a global table that gets replicated across a bunch of different regions. If you're looking for something that has high consistency, there's ways to get this to do that, but generally you probably want to look at another solution. Okay. Okay, so next we're going to talk about Redshift, database caching, and database migration tools. But we're going to pause here because we got like a minute left before we're going to go to lunch. Let me ask you a few questions. What is the name of the service that offers SQL databases? Good. What's the name of the subset of RDS that offers a specialized MySQL and Postgres variant that can also be serverless? Good, 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 good. Okay. What is the name of the type of consistency with DynamoDB that would have you check all copies of a data before you turn to response? Is that eventual or strong? Good. Good, Anastasia. Arpan, I see that. Strong. Excellent. Good. What's the name of the RDS function where you can actually create a copy of a database that it can only be read from. What is that called when you create a read copy of a database in RDS language? A read replica. Good, that's perfect. Excellent. Okay, so what service does RDS use underneath it to allocate capacity when you're not using the serverless version? What other service does it use, but you can't log into it? That's right, uses EC2 t-shirt sizes. Let me show you this one thing and then we'll go to lunch. Let's take 2 seconds. If we go back to ec2instances.info, that website that we used yesterday, I want you to know that there's RDS tab here. If you click on RDS, this will list all the RDS t-shirt sizes that you can use. Notice that a lot of these look very familiar because they look like EC2 t-shirt sizes. So just know that you can actually see the RDS sizes as well, including the processors, the storage, which most of them don't come with storage, et cetera, et cetera. Okay. So just know that this is here. I actually haven't seen this one before. This must be relatively new. Oh yeah, nice. Well done. Well done, Vantage. Okay. Any questions at all before we go to lunch?
Didn't you say RDS was managed? So we don't build servers? Why are we looking at servers?
Well, because you have to pick the size of your server, but you don't manage the server.
Oh, I see.
Yeah. Yeah, Alex. So you can see that the server is there in RDS, but you can't log into it or manage it or do anything to it. But you have to pick the size of database you want to run, which is based on the server size.
Right. Then it becomes invisible to you.
Exactly. Yeah.
Okay.
Yeah. So it's just for sizing purposes. You don't do anything else with it.
And serverless is the same?
Serverless allows you to set your boundaries, but for the most part, it's the same. Yeah.
Okay.
Cool. Thank you for asking, by the way. Okay. Well, you know, I like odd times. So it's 12:02 right now. So let's come back at 1:03. So I'll put up a timer for 61 minutes. When you come back, we'll finish the last 2 sections and we'll roll right into a lab. So we'll probably spend 15 or 20 minutes, then we'll do a lab. Okay. Enjoy lunch. Try to get some fresh air. Get away from your computer if you can. We'll see you in a little bit. Data warehouse service. Okay. So Redshift. So Redshift answers the question of what service should we use to house our data warehouse? Like we need to do large, OLAP analytical reporting. We need 3.2 petabytes of data in memory, that kind of thing. Well, this is where data warehousing, data lakes, that kind of thing are applicable. So we get information from our customers, from resource management, from transactions, other lines of business, and it aggregates into a data warehouse. Everything's structured and defined ahead of time for fast SQL queries that can be then parallelized and then aggregated to a certain level of detail. Amazon Redshift is the service, and it's actually based on Postgres 8.1, but it goes to petabyte scale. It was launched first in 2012 and really has just been a focus for data warehousing for Amazon for quite a long time. They've made a lot of changes to it. Basically, it has a primary node or a leader node that then basically coordinates with other compute nodes. It can read from S3. So using Redshift Spectrum, it can actually pull in S3 data. You can do all kinds of things, everything from like BI to operational analytics, predictive analytics, any kind of reporting. Basically, it's the analytics service. That's really what it's there for. It's the primary analytics warehouse. Now, the vast majority of databases optimized for row-based storage. So instead of storing data as rows, which is what most RDBMSs do, this one is actually organizing data by columns. So row-based systems are really great for transactional processing like OLTP. Column-based systems are really great for OLAP, for analytical processing. So when the query is analytics-based, queries often involve aggregating data performed over large data sets. So really only the columns are involved in those kind of aggregate queries. And column-based systems require fewer like inputs, outputs in order to achieve those aggregations if we focus on columns. So this improves query performance because really columnar data is actually stored sequentially on like the hard drives. So this also allows you to load less data into memory, which allows Redshift to perform more in-memory processing while running queries. So when you use that kind of columnar sorting, right, with the columnar storage, right, this permits the query processor to really rapidly filter out any large subsets of data that aren't applicable for the analytics that are being run. Cassandra, by the way, is another columnar KV store, but optimized for a different intention. Now, there are different kinds of concurrency scaling. So Redshift does offer the ability to support scalable concurrent users and queries with this concurrency scaling feature. So what will happen is that Redshift will add additional cluster capacity to process read queries as they're added in. So concurrency scaling is really achieved if the main cluster meets a specific set of requirements around like location, the different node types, and the node amounts. You can also specify further criteria around like the query type of queries that are being run to determine really if queries are routed to like a concurrency scaling cluster. So think of the main cluster, right, which basically allows you to like run kind of like your common queries. You can then scale out queries to a concurrency scaling cluster, which can be turned on like by using a workload manager. So basically queries get queued and they can then be distributed to other clusters as you need to. Now, if you do have a concurrency scaling cluster that's turned on, it's only used for the time that they're used. So like in this example, just to frame that up a little bit differently. So let's say a Redshift cluster has concurrency scaling turned on. The leader node here is going to receive a request that fits the requirements of being pushed over to a concurrency scaling queue. So the leader node is going to send a request to add a concurrency cluster because now there's something in the queue for that concurrency cluster. So Redshift's going to create a quick snapshot and store it into S3. It's going to allow the new cluster to access the data that it just quick cached via caching layer. As more queries arrive, if they keep coming in, then they're going to be submitted to that queue and they're going to be processed by that concurrency scale cluster. And the results as the queries are processed are delivered to the end user. When that concurrency scaling cluster is no longer needed, it's just going to be dropped while the main cluster stays online to handle queries. So you get to control which queries could go into a concurrency scaling cluster, leaving the main cluster untouched. The main purpose by which this is used is if you have a really high processing, long running query that you don't want interfering with your kind of like core main queries, like someone comes in and says, hey, I want to report for the entire year. You might push that to a concurrency scaling cluster and say, look, run that over there. Don't mess with my main cluster. So this is like the kind of things that Redshift can do, right? Parallelize queries, run them on separate clusters, quick run them on separate scaled copies of data. It allows you to get up to 3.2 petabytes of the cluster size if you need to run concurrent queries in parallel. In addition, Redshift has a few cluster types. So the node type, because this runs very similar to RDS in that there's like t-shirt sizes of EC2 nodes that run underneath it. You don't log into them, but they're there. The node type, by the way, determines whether, the CPU, the RAM, the storage, etc. There are different node types for the workloads. With RA3 nodes, you basically are optimizing for data warehouse hosting, whereas the DC nodes, like DC2s is the flavor in question. These are compute intensive nodes that have local SSDs, right? So this is used when you have more high performance queries versus kind of more low performance with larger data sets. So RA3 is really used for larger data sets that are low compute intensive. DC2 are dense compute nodes that are used for computationally intensive processing. It is generally recommended that RA3 nodes are used because they can handle more data, but if you need computationally dense nodes, you can use DC2s instead. So that's a little bit about Redshift. That's a rabbit hole, by the way, that goes a lot deeper than what we covered just for a single service. But that gives you the general idea of what Redshift is capable of. Oh, the other checkpoint is that if the data set's generally under like 1 terabyte uncompressed, DC2s are probably best for the performance and the price. RA3s are the best if your data is above a terabyte. I know you might say, well, who's using crunching data under a terabyte? I've been at actually Fortune 100 companies and they were like, big data is 1 terabyte. I don't know what the limit is, but Amazon draws that distinction. DC2s are for 1 terabyte or smaller data sets. Larger than that, you want to use the RA3 nodes. All right. So we've talked about RDS for like a managed database, DynamoDB for a NoSQL database, also managed, right? Highly managed. Redshift for data warehousing. What about caching? So for example, in our requirements for our user story at the beginning of this whole thing, Memcached was the open source analog they were using, right? But also know that Redis is supported as well, which Redis is pretty popular. So in this case, you've got a load balancer, you've got EC2 instances, and those EC2 instances are talking directly to the RDS database. What if instead you wanted to reduce load on that RDS engine for repeated queries? You instead can insert a cache into the equation. So, you know, this is where you have a side cache, which is a commonly known approach, right? These are general purpose caches that are kind of decoupled from the underlying data store. And they really actually help with read and write throughput, right? Depending on the workload and the durability requirements. Now there's a bunch of strategies here for how you get data loaded in. One way to get data loaded into that cache is to basically, you know, updates are made to the database without updating the cache. So what happens is that lazy loading ensures that the data loaded is only loaded once it's missed. So let me explain that in a little bit more detail to make sense here. Oh, it's good that labs are back. Oh, with that being said, let me, thank you for letting me know, by the way. Let me just fix this really quick. Because if labs are back, then we're going to do some labs. Yep, let me pre-warm that. I don't want any of us waiting. So in this particular case, what happens is the first thing that happens is that you go and try to talk to the cache, but the cache doesn't have the data you're looking for. So then what happens, right, is that you then go back to the database, you get the data, it comes back to the client, and then what ends up happening is that you then stick it into cache. So the reason you do that way is that the only data that gets loaded into cache is data that has missed the cache. So the first time you go to get it, it's going to be a little bit more expensive, but we're talking milliseconds typically. But the second time anybody else goes to get that same query, it's now in cache, because that's the first place you're going to look, is you're going to look in cache first. So this is called lazy loading. This means it only loads data when it's not in cache that is needed by the client. This is actually pretty efficient because it actually makes sure that the only data loaded is data that you need, but there is that first miss performance penalty. Contrast this with write through, where anytime the application makes an update to the database, it puts it in cache. The problem is that you could end up with data in cache that you don't need because it's actually not being used by the application, because you're writing everything there, but that doesn't mean it's being read, right? So this results in fewer cache misses, but requires additional storage for data, right? So it's really, the issue here is what's the impact of stale data on our use case? If the impact is high, then you probably want to do write through. If the impact is low, then just use lazy loading. There's also other strategies, you know, you could prefetch load an entire database regardless of writes. You could set a baseline if you wanted to. Now, Elasticache is the service that we use for this kind of caching. It is fully managed. It does support like nodes, right? Has a kind of t-shirt size. Very scalable, extreme performance. It has 2 engines. It's Redis and Memcached. Memcached and Redis, for the most part, are exactly the same except for 2 key differences. One, Redis can do advanced data like sorting, sets, and complex data types. It'll also do backup, restore, and multi-AZ. Redis will not do anything. Redis is a very simple cache, But one thing that's interesting about Redis Memcache that's different from Redis is that Memcache will actually thread and scale horizontally, which oddly enough, Redis won't do. Strange, but it won't. That doesn't stop people from choosing Redis, by the way. If you need advanced data capabilities like PubSub and sorting and stuff like that, then you're going to end up using Redis. Most people use Redis. Most people only use Memcache if they're just messing around. One other thing to note is that you can specify a time to live for your data so that it expires from your cache without you having to remove it. So it just disappears after whatever time. That could be seconds, it could be minutes, it could be days if you want it to be, right? By the way, if the data obviously isn't there, instead of loading old data, it'll just go over to the database. So how you manage this, by the way, is pretty much application side. So this is stuff that requires changes to your application. You can't just turn this on and automatically your application just starts using caching. You actually have to have some logic in your code to support this. Most database management library systems that you import into your code now will support a caching function and a read function and a write function as far as like exclusive paths for those particular database actions. So just know that most of the data management libraries now support this, but you have to turn it on. It doesn't happen automatically. Other things to think about that are useful for caching other than Elasticache is that DynamoDB actually has a millisecond accelerator. Did I say millisecond? I meant microsecond. A microsecond accelerator. And basically, you know, in most cases, DynamoDB will get to single-digit milliseconds of response time. If you need microsecond response times from your DynamoDB database, this is where you're going to stick a DAX cluster in front of your DynamoDB setup. This is a complete in-memory caching mechanism that sits in front of DynamoDB specifically. This is expensive in terms of total dollars, but incredibly valuable if you need microsecond response times. So it's actually a super incredibly useful tool if you need extreme performance against your DynamoDB database. Now, without DAX, there might be milliseconds that are causing response times, but if you need microseconds, you just throw DAX in there, and DAX is going to handle, especially for like microseconds for read-heavy workloads, right? Remember, this is not for writes. Writes go to the DynamoDB. This is for reads mainly. So just know that the DynamoDB accelerator exists. It will knock DynamoDB down to microseconds in terms of response time. That's the main thing to remember. Okay. Okay, last section, and then we're going to get hands-on. Well, I have some knowledge check and some questions to ask you. So let me make you think that we're going to be done with this quickly. So this is the question. How do we migrate our databases on-premise to on-cloud? How do we do that? First of all, the database migration service, which I don't know why they don't spell that out. Why do they call it DMS? That's horrible. DMS stands for Database Migration Service. It's actually listed as the Database Migration Service inside the console. They don't call it DMS inside the console. That would be confusing. So this is an agented system that runs on your database. It eats very little performance off the database, and it can one time or continuously replicate your data, right? Either in either direction, right? You can go over to cloud, you can go off of cloud into on-premise, it can be, right? But just so you know, either the target or the source database must be located on EC2 or RDS. It has to be on AWS. You can't migrate between two on-premise databases, by the way. Now, DMS will handle formatting of the source data for consumption by the target database, but it will not do any schema or code conversion. So just know that if you're going from MySQL to MySQL, there's no issue. If you want to go from MySQL to MSSQL, well, then you're going to have to use what's called the schema conversion tool. And again, they didn't spell it out. It's the schema conversion tool. Nowhere on the page. That's weird. Hold on, I gotta take a note of this. That's gotta get fixed. Okay, so the schema conversion tool. What this does is it allows you to convert from the databases on the left to the databases on the right. Not all of them can convert to all of them. So you have to read the documentation about the schema conversion tool. But like, for example, like Oracle can be converted to a bunch of the RDBMSs, no problem. Greenplum can go to Postgres. There's a bunch here. Yeah. So read the documentation, but a schema conversion tool can help you convert a schema from one database type to another. Notice that DynamoDB is listed there. Not everything can convert easily over into DynamoDB. The more complex and clunky your database is, as far as like stored procedures and code embedded, the more difficult it's going to be for the conversion tool to work. Oddly enough, this works surprisingly well for schema conversion. It's kind of shocking, frankly. All right. So we just took a journey through RDS, DynamoDB, through Redshift, through caching, which is mainly Elasticache, and then a little bit about the database migration services. That's what we did. So riddle me this. What is the benefit of using RDS in a multi-AZ configuration? What does multi-AZ do? Mr. Nazim, SEB, good. Patrick, good. So yeah, so it does provide automatic failover across availability zones. It certainly doesn't eliminate the need for read replicas, right? It doesn't provide cross-region replication. And it doesn't deliver 2 live copies. Just so you know, only 1 copy of the database is live at a time. So in a multi-AZ configuration, there's 1 primary who's open. The secondary cannot be touched or queried in any way, shape, or form. So just letting you know. The reason for that, by the way, is that when you put databases in synchronous replication, if you slow down the second database, it'll slow down the first database because they're in sync with each other. So Amazon doesn't let you access the second system because if you slow it down or mess with it and like decide to run reports on it or whatever, it'll slow the first database down, which is the one that is taking traffic. Okay, what type of Elasticache offering offers advanced sorting, ranking capabilities, pub sub, backups, and multi-AZ failover? Which one of those? What, no one's gonna say C? Isn't lazy loading Amazon's latest offering for procrastination as a service? No, I see that you all put A. That's perfect, right? Redis, yeah, that's dead on the mark. Okay. Which of the following is true regarding DynamoDB global tables? Why would we have global tables? What's the #1 reason for it? Right? It's about location, isn't it? So then what would be the answer here? We want global tables because we want them to be global, which means we want them in different physical locations, which means tables can be in different AWS regions, right? Excellent. Good, Aaron. Okay, what type of storage does Amazon Redshift use? Okay, I waxed poetical on this. There we go. Yeah, columnar storage, right? Not row storage, columnar storage. Excellent. Well done. Okay, which of the following is true regarding an Aurora database? It makes 100 copies of your data. No, that's not true. Good. Yeah, I mean, there's only 2 databases it's compatible with from that perspective, right? So MySQL and Postgres. So those are your friends. So yeah, I love that. 9 copies of the data stored across 3 availability zones. Just, that one's 6, of course, right? By the way, are multi-availability zone deployments for anything not required for high availability? I mean, just say this. Amazon advocates that for every single service, you need to run it across multiple availability zones for high availability. So the answer to that is no. Everything requires high availability, which means to define that, that means your services have to span 2 availability zones. With managed services like DynamoDB and S3, that happens for you automatically. For other services, you got to read the fine print. RDS doesn't do that for you by default. Postgres doesn't do it either. Sorry, Redshift doesn't do it either. Neither does Elasticache. So just know that if the service uses the concepts of nodes, EC2 virtual machines, instances, if it uses virtual machines as the underlying separator, then it's got to be set to multi-AZ. It won't do it automatically. If it is truly serverless, as you heard Alex and I waxing about earlier, if it's truly serverless, which means hidden servers, then it's already multi-AZ, so you don't need to worry about that.
And why give
In-
us a choice?
Say again?
Point of not doing this automatically? If like
In other words,
so
why
is
would
that-
they even bother doing that, right?
Yeah, like isn't that again just to confuse you?
No, it's because most of the services that do that offer nodes and whatnot, are older services. So all the newer services that Amazon launches, by default, most of them are highly managed, which means you don't have to worry about that. And don't let me throw you off. DynamoDB is one of the oldest services, but most of the newer services are highly managed, and so they do that for you by default because they know that's what customers want. The other restriction, though, Alex, is the technology. Like an RDBMS, it's really hard to set it up to be like technology-wise to be multi-AZ, because you have to then support clustering, which is really complicated based on the technology. But your question is then why don't they just force you to do multi-AZ for your databases? Why even give you the option of clicking a checkbox?
I do not
Cost.
want high availability. Like,
What if it's not production? What if it's a proof of concept?
Is it
So-
more expensive to do with multi-AZ?
Say again?
Even if it's test, who cares? Just
Well, because it costs more.
that was my question.
Yeah, sorry, that's the thing. The cost is the differentiator.
All right,
That's why
so
they threw it in.
it does incur a cost.
Sorry, I must have missed that. You were breaking up for me. I apologize. Yeah, so cost is the differentiating factor. Oh, that's probably worth saying. So billing and security are the harder things to kind of like, not hard, but harder to manage inside of any cloud provider. And the problem is that every design decision and every toggle and every configuration has either a cost or a security implication. Most of the time it has both, right? So just know that checkbox for multi-AZ has a cost implication. So that's why. Module 6, we're here. Okay, so let's talk about labs. So because it's 1:30, so we're 30 minutes in. So let's take a run at this. By the way, this is a 30-minute lab, so it's short and sweet for the most part. So in this lab, what we're going to do is that we are going to install an RDS database. So you're going to see it on the upper right-hand side under the private subnet. Databases are rarely, if ever, stuck across the internet. They are not designed to defend themselves from internet traffic. So just FYI. Then we're going to create an application load balancer, which is that thing you see on the lower left-hand side. A load balancer is used to distribute traffic. So you're going to define load balancer targets and rules to the private subnet, which is kind of interesting because we haven't even covered the second module yet on load balancers, but we were going to set one up. And then we're going to test connectivity to the EC2 instance through the load balancer. And then we're going to test connectivity to the database using the console. Now notice there's a NAT gateway there, just in case the database needs to get out. I'm not really sure. Oh, it's because the EC2 instance is on a private subnet. So that's why it's there. Gotcha.
And you're absolutely sure that if this Amazon EC2 was an app server, for example, an application running, and you wanted to stick a web server in front of it, you would not put it in the public subnet.
That's correct.
You would put the web server and the application server in the private subnet.
Well, they could be in separate private subnets, but you could put them in the same private subnet too. But yes, they would be private. Yeah. That is standard practice now. Okay. And there's the thing I just actually verbalized. RDS instance, load balancer target rules, EC2, right? So they're giving you a little bit of a preview around the application load balancer, which is something we're going to talk about in next modules. Okay. So to quick labs. Oh, look at that. 16 labs are ready to go. So in this lab, it's exactly as stated. You're going to create a database, create and configure a load balancer, review the like instance metadata of the actual like t-shirt size EC2 instance that you can't really touch for RDS that you set there. They're going to test application connectivity, and they're going to create an RDS read replica, which is an optional task, but you're going to put the read replica in a different region, which is kind of fun actually. So here we go. That's what we're doing. So go ahead and click on Start Lab in the upper left-hand side, get cracking, and I will be quiet. If you have any questions, let me know. Otherwise, let's do it.
Doesn't it say hour and a half? Oh no, 129.
Well, Anastasia, what they do is they give you 2 to 3 times the time that you need, just in case you step away or run into a problem.
Gotcha.
Yeah. So they do that for all the labs. I don't know if you noticed, but like we did a 45-minute lab the other day, and I think it had an hour and a half of time.
Mhm.
And I actually asked Quick Labs about this, and they're like, yeah, we give you extra time just in case you get distracted. I was like, okay.
Got it.
I was like, that's nice. Probably helpful if I share my screen. All right, so here we are on a journey. We have spent some time finishing up some compute. We've done database services and storage, excuse me. So lift my desk up. And so now we're going to talk about monitoring and scaling. First things first, though, per the usual, let's check in. All right, so what factors impact your decisions for making your workload scalable? Well, someone tell me. Would you like to make all of your workload scalable? Sure. E, all of the above? Yeah. I would say that usage patterns are probably the number one thing, but here's the problem. Most of the time we don't know the usage patterns until it fails. And so then once it fails, I feel like I have an idea of the usage pattern, and then I start adding scalability in. Well, the funny thing is that most companies aren't willing to pay for scalability up front unless they know they're going to get hit with a bunch of users. So criticality of the workload is rarely used as a reason to not scale. In my experience, it can be like if it's like non-production. Anybody else have a different experience? Any other factors that aren't listed here? I gave you one factor that's not listed here. Time. How many times have you been working on a project and you're like, oh my God, like there's like 5 features that have to get done and you got to drop a feature to get something done. One of those, like if you're in deployment, could be scalability. Sometimes that gets dropped for day one. Okay. All right. All right, so let's talk about monitoring and scaling. So we're back to our stakeholder feedback, which is everything starts with monitoring and logging. I mean, as you know, you really can't measure something that you're not monitoring. And it's really, it's difficult to manage something without some data, right? So we have to know how to set alarms, how to initiate responses, to create self-healing architectures. What does AWS have in terms of load balancers? If I want to distribute traffic, how can I support that? What does it have in terms of monitors and alarms and whatnot? How can we optimize resources with demand? How can we match capacity and demand, right? How do we prevent things from getting overloaded? How can we be elastic in our usage of cloud? Because why do we come to cloud if we were not going to be elastic? If we're going to run resources the same way we did in our data center, why did we even bother going to cloud? That's just going to make AWS, for example, expensive data center 2.0. So what tools and services are available to monitor and log activity in AWS accounts? How can you set thresholds and be alerted to changes in infrastructure? How do I add high availability to virtual machines? And also, by the way, to really any application type. How do you dynamically increase and decrease capacity to meet changing demands? So this is where things shift because we're really only focused on a couple of things here. First, everything related to monitoring. This is to trigger events actually, but related to monitoring. And then auto scaling and load distribution happen here. Just to highlight this, this is the trifecta of items that work together to make virtual machines elastic. These three components right here, CloudWatch, auto scaling, and elastic load balancing is the trifecta that makes your virtual machine scale up and scale down. It's even useful if you have one virtual machine. Let's say it's a build server, and if it goes down, you want it to restore itself. Well, you can put it into an auto scaling group of one, put a load balancer in front of it in case it decides to move around. And then you can put your Jenkins server, for example, or your GitLab server in that auto scaling group. And if it fails, it'll recreate it, assuming that you have an automated way to restore backups. In most cases, by the way, just put the home directory on EFS. Solves that problem. So just know that that's the trifecta. Elastic load balancing, auto scaling, and CloudWatch work together to make these things happen. Now, here are the various solutions for monitoring, event response, load balancing, and auto scaling. This is how we get there. So the monitoring using story says, I had a failure and I don't really know what's going on, so I need more data. How do I get more data? Either monitoring data or logging data. How do I get that? Well, there's a couple of ways to do this, but there's a couple of reasons why to do it. So you have to know in AWS where to find information to get the data you need. It's like a Sherlock Holmes, data, cannot make bricks without clay, right? So I need data. So the reasons for monitoring are multifold, but basically it comes down to two things, right? Operations and security. That's really what it comes down to. Because operations, don't get me wrong, this could be DevOps, SRE, DevSecOps, whatever you want to call it, Triceratops. But we're really talking about, is the system up? Is it performing? Is it feeding user data out? Are all the components working? Is there a slowdown, a bottleneck, a choke point? And that's all operational. The other piece is someone trying to hack us? Have we been hacked? How do we respond if we've been hacked? How do we prevent hacking? That's the other piece. Now, CloudWatch as a service is got about 11 sub-services underneath it. Its sole focus is metrics. That's what it does. Nothing else. It is basically to handle metrics. It's got logs, don't get me wrong. It's got events, don't get me wrong. It's got like insights and data, but its main thing is it's a metrics repository and it's used for monitoring. So it collects information, monitoring and logging information. You can monitor it, you can respond, you can analyze, you can generate reports. So CloudWatch, by the way, can go to 1 second granularity on dashboards, and it can retain up to 15 months of metric storage and retention. CloudWatch is a great product, but I gotta tell you, most people don't like it because when you get to certain points of scale, it's not as good as the third party. I know that's a horrible thing to say. CloudWatch is the native integration monitoring and metrics tool, but when you get certain points of scale, a third party is probably gonna be better for you pulling your data out of AWS. But I gotta tell you, nothing will beat CloudWatch for its integration, including its event integration and like create a self-healing infrastructure. By the way, CloudWatch will track everything that AWS can see. If you start an operating system, it can't see what the operating system by default thinks is the percentage of consumed disk. It cannot see what the operating system says is the percentage of consumed memory. Now, don't get me wrong, AWS can see that it gave the box 4 gigs of memory, but only the operating system knows how much of that memory it's using. So if you want metrics from another system, like a database system or a operating system or a Kubernetes system, like a container orchestrator, you've got to put an agent in there. CloudWatch has an agent. You can install it. It's actually on the Amazon Linux image by default. You just turn it on. And so just know that there's some things that Amazon can't see because they're system specific. So you got to turn those on. But everything else by default, when you run Lambda, it shows up in CloudWatch. You run DynamoDB, it shows up in CloudWatch. The minute you run a service in AWS, it's going to show up in CloudWatch. So in this case, you can trigger a response of auto scaling. You could send a notification. You can do all kinds of cool stuff with CloudWatch to make sure that your metrics are being acted upon. You can also send custom data, by the way. You can also send logs, right? So just to be clear, though, there's about really more than this. There's about 6 kind of logs that you can actually get inside of AWS. Most important is that CloudTrail is going to track AWS activity against your account. It's not going to track your systems. It's not a metrics log. It's API activity. If someone logs in as the root user, that's a CloudTrail entry. If someone logs into your operating system and you're tracking that, that's a CloudWatch logs entry. If someone tries to traverse your network and get into your system, you want to see how that flows across your network, that's a VPC flow log. If you want to just send your application logs to CloudWatch logs because you want to use it for insights, that's a custom log. So just know you can send all the custom logs that you want, but what will happen is that there will be some aggregation that you can control. It will write to a log group, and then it will store metrics if you ask to pull them out inside CloudWatch. You can then set an alarm against your logs and have it trigger all kinds of stuff, a notification, auto scaling. You can control that if you want to. Sorry, Google started talking to me about the temperature in the house. So that's CloudWatch logs, which can store any logs that you want to send it. CloudTrail writes its own logs because it captures every API call made against your AWS account. This includes anything in the console, anything in CLI, any of that stuff. It can write it, by the way, to an S3 bucket, or it can write it just into CloudWatch logs if you want to. So remember, CloudTrail is for AWS calls made against your AWS account. Here's some example of things you can track in CloudTrail. Who shut down an instance? Who changed the security group configuration? What permissions were denied? Like who did what or tried to do what? Here's an example. Here's a user identity, and the username Alice tried to do something to an instance ID. What was it they tried to do? Well, if we look, they tried to stop an instance, and they tried to do it in US West 2. Questions about that? Now that's what they sent. Here was the response. Oh, go ahead.
Is there a time limit for when the logs, for how long logs are accessible? Are they?
Oh, you mean in CloudTrail or in CloudWatch?
Yeah, both actually.
Well, it depends on where you store them, right? So if you store them in S3, then that's up to you. You determine how long you want to keep them for. If they're in CloudWatch, like metrics, for example, are stored for 15 months. In CloudWatch logs, I believe it does aggregation after certain periods of time. I think it's 18 months in for CloudWatch logs, but I'd have to look that up. But it's months. It's a long time. If you want to externalize it, by the way, to S3, you can do that for all the services. And once it's there, it's your discretion. VPC flow logs, as a contrast to CloudTrail logs, CloudTrail captures API calls, flow logs captures all the network traffic that is flowing across your VPCs and your subnets. So if something is coming into your system, it'll tell you where it's going, right? Flow logs, by the way, are turned off by default. Flow logs also can be published either to S3 buckets or to a CloudWatch log group. So data, by the way, is collected outside of your network traffic, so it's not going to affect your throughput or latency. You can diagnose like restrictive security groups or monitor traffic or determine the direction traffic is going. So yeah, easy to figure this out. Easy to figure this out. Let me clarify that. VPC flow logs can really help you in troubleshooting if you're trying to figure out what's going on inside your network, because like you can't ping something or you can't see something. It can tell you why the ping is failing. It can tell you why you can't get web server traffic. It'll let you know like what's going on at a network level. Here's a flow log record. So notice it lists your account, the interface ID, the source ports and destinations, the protocol that was used. Notice at the bottom of the action, it says accept, means it wasn't rejected by something. It's not going to include, by the way, DNS resolution traffic or DHCP request, if you're familiar with that. If you're running your own DNS server, you can see it, but if you're running it, if you're using on AWS's, you're not going to see that. So just FYI. If you publish flow logs to CloudWatch, it just goes into a CloudWatch log group. And so the NICs, are the separated logs. So it does it by network interface. If you publish it to S3, does the same thing, right? So flow logs are basically published to the S3 bucket that you specify. It separates it by NIC that's being monitored. The maximum file size is like 75 megs. It'll just stop adding records to it and then publish the file to S3. So it publishes logs to S3 in a 5-minute increments. So it'll take you 5 minutes if you're publishing to S3 to see it. If you're doing log streams, it'll just show up as soon as it gets published, so usually within a second or two. Okay. So the main thing to note is that there's a bunch of different logs that you can publish. CloudTrail, right? CloudWatch can receive logs. CloudTrail will publish logs. VPC flow logs will allow you to troubleshoot your VPC networking. So all of this that we saw at the beginning. Where are we? There we go. Okay. Let's talk about invoking events. What if you need to be notified and you want a response if all of a sudden you're getting latency errors, right? As an example, or in this case, HTTP errors. So in this case, what happens is based on metric data or even logs converted into metrics, you can create an alarm which can trigger a response. A metric alarm is going to watch a single CloudWatch metric, but you can set it so if it has to, like, let's say, for example, CPU has to be at 90% for 5 minutes. So that's 5 consecutive times before you respond. If it just pops up above 90% for a second, like who cares? But if it does it for 2, 3, 4, 5 minutes, then you can set an alarm that says, hey, it's been over 90% at 5 minutes. Let's add some capacity to relieve this, right? Alarms have 3 distinct possibilities. The threshold's either been exceeded, it's not been exceeded, or there's not enough data to know whether or not it's been exceeded because you either lost access to the data or it's just getting started. Usually insufficient data only shows up when you first start capturing a metric or if there's an error with AWS. So it doesn't happen that often, frankly. Here, by the way, you have a statistical graph of your like published metrics. So you can actually see what the alarm is going to alarm on. So it will show you the threshold and show you, like, for example, hey, I didn't have 3 consecutive breaks of the threshold, so I didn't alarm, right? So just know that you can actually see exactly what CloudWatch is seeing and what the threshold alarm is, right, for that. So in this particular case, the alarm is going to trigger if it's sustained over 2 time periods. So it didn't happen the first time, but it happened the second time because there were two over the threshold periods. Now, CloudWatch has a subservice called CloudWatch Events, which has been used so much for event-driven architectures that Amazon is now making it its own product called EventBridge. So CloudWatch can be used to trigger a response because CloudWatch can call Lambda. It can also call SNS and other things, but once it gets to Lambda, it can pretty much do anything it wants to, right? So in this particular case, it's can be extended to be more of an automated workflow instead of just kind of a one-off trigger, which is what EventBridge is, right? EventBridge is trying to trigger an orchestrated workflow of responses in the event of some kind of infrastructure issue. Here's an example of EventBridge, right? Let's say that you've got a bunch of applications, events, and services. What they can do is that they can actually trigger into an event bus, which is what EventBridge is acting as. And then what it can do is, based on rules, it can deliver a stream of real-time data from whatever event sources are going on the left-hand side and send it to targets such as Lambda or to Datadog, which is a monitoring service, or PagerDuty, which is a pager service, or Zendesk, which is a help desk service. These are all third parties, by the way. So this is the core, is these event buses are the core of EventBridge. So if you're familiar with how CloudWatch Events works, the default event bus, it's the same thing. You just create this bus that sends information based on rules to certain services or third parties inside of AWS. So EventBridge is kind of a powerful new player because people were using CloudWatch Events to try all these event-driven infrastructures. And so they decided to actually spin it off as its own product called EventBridge. Here, by the way, what happens is that EventBridge removes the friction of like writing point-to-point integrations. So like it basically allows you to mirror changes in AWS and point them to third parties or through notification or through API calls. So think of this like a Zapier, or God, what are those other integration points where it's like, I have something happen in AWS and I want to let a third party service know. EventBridge is how you do that integration. So it'll do event ingestion as well as event notification and delivery. And so that's what we use EventBridge for. Any questions about any of that? Either about CloudTrail, CloudWatch Events, EventBridge. Okay, let's talk about these last two pieces and then we'll actually get some hands-on. So load balancing is actually a pretty large topic. So load balancing, which we saw in the previous lab, is just the ability for us to distribute traffic to certain servers in target groups. Now, if you're using an application load balancer, it doesn't have to be a server, it could be a Lambda function. So traffic is forwarded to these targets based on pathing. And this is what an application load balancer does. A network load balancer and a gateway load balancer don't do this. This is just an application load balancer, which is what we were running. Notice at the bottom left, it says example.com. Then we've got example.com/blog. Then we have example.com/mobile. This is what a load balancer does, is that it can actually look at the traffic suffix and send you to whatever target groups you want to send it. So if you've got a desktop and a mobile site, you can do that differently than if you have an Americas site versus an EU site versus an African site versus an Asian site. Like you can just vary that up. How come we never talk about Antarctica? Isn't that a great continent? Anyway, moving on. So an ELB, of which an application load balancer, a network load balancer, and a gateway load balancer are all flavors of elastic load balancing, because Amazon loves the word elastic. So we all have to live with that. But it allows you to distribute traffic across multiple backends. And the load balancer is the only thing that has to be public if you want to keep everything else private, right? And that's true for the network and application load balancer. Gateway load balancers are more like security devices. So they are the youngest of the load balancers. They just came out within the last year. Here are the different types: application, network, and gateway. Just to say this, most people don't use Classic anymore. It's supposed to be retired, and it's really for the EC2 Classic network, which is going to be retired in August of 2023 or 2022. I can't remember. Sometime within the next year or two. So people have just been given plenty of warning. So that Classic load balancer is going to go away. So try not to use it if you can. Here are the differences, and mainly just ignore the gateway load balancer. This basically does advanced load balancing of traffic, but more at a like layer 3 level, more for security. So an application load balancer can actually like redirect traffic, filter it, parse it, and assign it to different target groups. It can also give fixed responses. The network load balancer, the second one on the left-hand side, that one is a very simple load balancer that can handle hundreds of thousands of connections per second, but it literally just operates off of a port, a socket. So IP address and port. By the way, notice that it says that the network load balancer can have statics and the ALBs cannot. As of today, the application load, well, a couple of weeks ago, the application load balancer can also have a static IP address. So it's now, the NLB is now not the only one that can have a static IP address. Both the ALB and the NLB can both have static IP addresses now. Notice that the gateway load balancer is really just, in a sense, a filter or scanner. It can actually like redirect traffic, but it's not really like a traditional load balancer. This is where your like deep packet inspection and other security functions are going to show up as in the gateway load balancer. And the classic load balancer, just forget about that one. I don't even know why it's still here, why we're still talking about it. Unless you have a really specialized edge case, which, you know, talk to your Amazon rep if that's the case, but most of us aren't going to use the classic load balancer. Those are just the load balancers. So ALBs, NLBs, GLBs, and then the old one, the CLB. Application load balancers can not handle as many requests per second, but they are more intelligent in terms of pathing and routing. Network load balancers are simple load balancers that can handle hundreds of thousands of connections per second, but they don't have any pathing capability. GLBs allows you to basically boot third parties into your network flow. So if you want to insert security taps or deep packet inspection or advanced routing capabilities into with a third party system, that's what the gateway load balancer is that it brings in a third party like a Fortinet, you know, those kind of things, right? So you can bring firewalls and deep packet inspectors in. Questions about load balancers? Whoa. No response to my evil laugh. Okay. Let's talk about auto scaling. So let's say that you want your web servers to scale up and down in terms of number automatically, because we don't want to get overloaded, right? So you want to be able to go to 500 to 1,000 if you need them, because your Facebook. Well, Facebook runs more than that, but you get the idea. So auto scaling basically allows you to support that elasticity of adding horizontal scaling. And by the way, you can run internal auto scaling groups. You can run external, like they can be public or private. It doesn't really matter. That doesn't really matter to auto scaling. Now, how auto scaling works is that basically auto scaling adjusts capacity to minimums and maximums based on what you've told it. Now, just so we're clear, auto scaling exists for more than just virtual machines. You can do it for databases and for Aurora and other things. So like it even mentions that there's multiple services that have auto scaling or on-demand provisioning. But then there's EC2 auto scaling, which allows you to handle elasticity as well. So just know the concept of auto scaling isn't just for virtual machines. It's also for a lot of services. Like I think you saw that even with Aurora, is that you can set it to on-demand provisioning, which is auto-scaling, really. Well, provision through, but it's on-demand is really on auto-scaling. Now, the idea here is you've got predicted demand, and then you've got hardware expenditures, which is what we should traditionally did in a data center, is you'd have to buy large investments of hardware over time to make this function. But here's the funky thing. Actual demand could really cross those hardware boundaries really easy. And so you want to be able to keep demand and capacity just in relationship to each other. And so you've missed some opportunity if you have that much extra capacity. And of course, this means the users are having a bad experience. So you've lost revenue and reputation there. So you'd rather have it be this, where they just stay in relationship to each other the entire time. Now, managed services, it's real easy to enable auto scaling. You just click a box and usually just fire and forget, let it go. EC2 is a little different. EC2 has 3 components. You have to have a launch configuration or a launch template. You have to have an auto scaling group definition, and then an auto scaling policy in order for this to work. Now, before you can create an auto scaling group using a launch template, you have to basically specify the template, right, that contains the AMI, the instance types, security groups, what are the roles or permissions. And even though they have launch configurations and launch templates here, I'm just going to tell you right now, please, please, please use launch templates. Please do not use launch configurations, right? So the reason is that launch templates have all of the modern features, kind of like a modern load balancer. Launch configurations are older ways of launching auto scaling groups. And it's like a classic load balancer. It's going to get retired at some point in time, and it does not have all the advanced features in it. So try to use templates whenever possible. Now, once you've defined a launch template, what you can do then is that you can then define an auto scaling group. The auto scaling group says, which load balancer are we using? What's the maximum and the minimum number of instances I can use? And where would you like to start? What's your desired number? And then once you've defined all the components of your auto scaling group, you then have to have a scaling policy. So you've defined a launch template, you defined an auto scaling group definition. What's your scaling policy? Now, scaling policies come in 3 flavors: scheduled, dynamic, and predictive. What's weird about this is that dynamic has a couple of subflavors, like step scaling or target tracking. There's a bunch of components to this, right? So again, the launch template is our recommended thing that we recommend that you use instead of launch configurations. This includes all the details necessary to launch an EC2 instance. And then you create an auto scaling group, which has your minimums, your maximums, and your desired, right? It also, by the way, will terminate instances that fail, relaunch new ones, right? Notice in this case, there's 1 minimum and 4 maximums. The desired is 2. So it's going to create 2, but it'll go all the way up to 4 if it needs to, based on what numbers you say are important. How does it know which numbers are important? That gets defined here in the auto scaling policy. The auto scaling policy says, do I want to keep everybody at 90% CPU utilization? Do you want to keep everybody around 85% memory utilization? Do I want to make sure that latency stays at 100 milliseconds? These are the alarms and the metrics that you define, and auto scaling will try and keep it near those numbers. Now, auto scaling policies, as mentioned before, comes in 3 flavors. Scheduled, which means, hey, at 8 a.m., just double capacity. Dynamic, which says, hey, I want you to keep CPU utilization at 90% for all my boxes, and I want you to keep memory utilization at 85%, and I want you to keep latency at 100 milliseconds, not more. Dynamic can do that. That's called target tracking. Predictive scaling actually looks at your past history of metrics in CloudWatch and figures out how you need to scale based on the metrics you define. Predictive only works if you've got metrics, historical metrics to use. If you don't have it, you're probably going to use dynamic, honestly. Now you can optimize costs with auto scaling, because consider this. If it's 3 o'clock in the morning on a Saturday morning, and most of your customers in North America, you're probably not going to have a whole lot of people on your service. I could be wrong. So maybe you go down to business continuity minimums and you only run 2 servers. But let's say it's Tuesday at 10 a.m. and that's your peak day, and you're going to run 100 servers. You could literally scale down to 2 on Saturday and Sunday morning and scale up to 100 on Tuesday. In other words, you can actually set it up the way you want it, your scaling policies. In addition, when you run an auto scaling group that has EC2 virtual machines inside of it, you can actually make it so that they use different instance types to optimize for costs. This is great for you because we can now launch our web servers and use a small percentage of reserved instances, a lot of spot instances, which are up to 90% discounted, and some on demand if the spot instances get choked out for whatever reason. This allows you to automatically, without having to touch anything, optimize your cost based on the best licensing type that you can support. So just know that auto scaling allows you to automate your cost optimizations as well, because you can create mixed fleets of instances based on the level of interruption you can withstand. So can be very useful. So just know, by the way, with auto scaling that some architectures need to scale on multiple dimensions of metrics. You want to be aggressive about scaling out and conservative about scaling in, and try to automate this. If you don't automate this, you might as well not even use it. If you're not automating this, don't even bother. All of this needs to be automated. You're not going to get in there and manually turn the dial, right? Unless you're just going to sit there and watch the system the entire time. Because by the time you get the page, the notification, the text, and you respond, the load issue might be over. So try to automatically set this up, because that's what it's designed for. Questions? Okay. Little knowledge check. Which of these is a valid target in a target group for an application load balancer? Which of these is actually something you can actually target behind an ALB? Yep, EC2. If it said Lambda up there, that could be another option, but it's not listed. Okay, if you have an application with unpredictable traffic patterns that runs on at least 2 instances, and you want the CPU utilization to stay at around 75%, which EC2 auto scaling strategy should you choose? Which one did I say had target tracking inside of it? It wasn't scheduled. So which of the others? That's right. And by the way, unpredictable traffic patterns are not great for predictive, because history doesn't matter at that point. Good. What service can invoke actions based on data from account resources and support third-party management services? Which one did I say was the best for third-party integrations? Yeah, EventBridge. That's literally what it's designed for, third-party really integrations. Excellent. Which of these 2 are valid alarm states in CloudWatch? So notice that OK isn't there. What are the other 2? I said one would show up when you cross the threshold. Another would show up if you didn't have enough information. So, excellent. So C and D, right? Alarm thresholds, because threshold's been crossed, and the other ones, I don't have enough information, so I don't know what you're asking. What is a typical use case for CloudTrail data? Well, pretty sure it's not observability, so it's not going to be A. What about the others? Remember, I joked about this, about being able to capture certain types of logins. So that would be store log data and then capture root login failures. Logging events for a particular service or application, well, that's CloudWatch, not CloudTrail. I know the names could be more distinct, but they're not. All right, this is the end of module 7. A couple things are going to happen now. One, we're going to spend some time doing this next lab. So in this case, we're actually going to inspect our existing environment, which is actually being provisioned as we speak. We're going to create a launch template. And then we're going to test our application. I'm sorry, create an auto scaling group. So we're going to create an auto scaling group, test the application in the auto scaling group, and then we're just going to configure some high availability options. So in terms of labs, okay. Let's take a look at this thing. In terms of labs, inspect your existing lab environment. We're going to use the launch template because remember, that's better than a launch configuration. We're going to create an auto scaling group, test the app, test the high availability of the application tier, configure high availability for the database tier, which is going to be fun. And then we're going to make the NAT gateway highly available. And then we're going to test the high availability of the Aurora database that we added earlier. That's it. So that's what we're going to do with this particular lab. This lab is usually allocated about 45 minutes to complete. So it's about 2:54 right now. So we're going to check in closer to like, you know, a little after 3:30 or whatnot. But we're going to run pretty much until 4:45. So my recommendation is that let's get running on this lab. So go ahead and hit the start button. And then please let me know the green checkbox if when you're done. And if you have any challenges, just let me know. I am probably going to step away at about 2:30 for about 10 minutes. And I highly encourage you to do the same. But otherwise, let's get cracking on this lab. I will be right back. automation on AWS, which is our next topic, is actually fairly straightforward. There's a lot of third-party tools to manipulate AWS, but there's really only one kind of integrated tool, which is namely CloudFormation and the Cloud Development Kit, which basically just takes code and converts it into CloudFormation. So we are going to talk about how automation functions. And since it's an API-driven infrastructure, automation should be key for everything we do. So let's check in first. So really the question is that have you used any of these tools like Terraform, Pulumi, Elastic Beanstalk, CloudFormation? Has anyone used these tools? Terraform? Yeah, me too. Elastic Beanstalk, by the way, is not really an automation tool. It's like a wizard for EC2. So I'm not sure why it's listed here, but Pulumi would be another good option. You know, if you wanted to use the Python libraries natively like Bodo, that would make sense too. Terraform is by far the most popular tool for orchestrating infrastructure because it is cross-platform to a certain degree. I just taught a class on Terraform last week, and the funny thing about Terraform is that you have to write a configuration file per cloud provider, so it's not really multi-cloud. It can support multi-cloud, but you do have to configure it every single time. So it's not like you can write it once and run it anywhere. It's not, what was that, Java, right? All right. So the CTO comes back to us and says, hey, you know what, cloud architects, we need agility. Our way at building infrastructure for our workloads is not fast enough, and we have to focus on infrastructure as code. It's really a key to our success. How can we automate resource creation? How do we get started with CloudFormation? What are the primary components of a CloudFormation template? Let's see how it works inside of AWS first. Fair enough. How can I simplify our cloud infrastructure build? Is it possible to manage multiple sources as a single unit? And how do we deploy web applications at scale? So Amazon's going to frame this up as if like you can do it yourself with CloudFormation and EC2, and then there's a higher level of abstraction with Elastic Beanstalk. Really kind of a weird way to frame this up, because CloudFormation should just come out of there at this point. Either you're going to roll your own with EC2 or you're going to use Elastic Beanstalk. But just to say this, CloudFormation could be used for both EC2 and for Elastic Beanstalk. So it's a little confusing because you probably just wouldn't roll Elastic Beanstalk all by yourself. Anyway, it's not infrastructure as code, so that doesn't really meet our objectives to have this service listed here, frankly. But moving on. So Elastic Beanstalk is a wizard that allows you to just give your code, and then it will deploy simple, scalable web architectures like applications and services using best practices. Beanstalk is a great place to start. It is not a great place to stay. Can't tell you how many people I've talked to over the years have had to migrate off of Beanstalk. So, you know, it will do automatically scale your application. It'll do blue-green deployments. It'll do immutable deployments. It'll do all kinds of cool stuff, but it's not really where you stay unless you just are POCing or you don't really have anybody who can do infrastructure. That's really the truth. So think of it as a wizard for EC2 that follows best practices. That's really a good way to describe it. Now, there are solutions here for managing systems, both through CloudFormation, which basically provisions infrastructure, and from Systems Manager, which can automate the running and managing of infrastructure. Now, Systems Manager seemingly is focused on EC2, but just know you can automate a whole bunch of other functions as well, services as well, in addition to EC2. But let's talk about CloudFormation first. So CloudFormation, you use this when you want to deploy a development environment in other regions without redoing the work. That's true. When you want repeatability, that's it. Now, portions of this are all about how CloudFormation is infrastructure as code, the resource stacks that CloudFormation creates when you give it a file. These files, by the way, are known as CloudFormation templates. Various ways to get solutions implementations and various ways to increase your programming applicability. Like if you want to code, instead of learning how to do CloudFormation, you can just code if you know Python or Ruby or whatever, whatever your language is, TypeScript. So infrastructure as code focuses on you being able to do things out of a repository with files in it. And those files can get versioned. So a CloudFormation template, as an example, is a text file that describes the resources you want to create and how you create them. So it's a little weird, but like in a single file, you can actually define an entire infrastructure from VPCs to internet gateways to all this other stuff. Let me give you an example of what one of these files would look like. I think I have one that I was working on actually, or at least one that I was messing with. Oh yeah, there it is. So I know this looks like, huh, that's weird. Huh, that's weird. Okay, whatever. Well, let me blow this up. That's very strange. Hold on. Usually this is what works. Huh, okay. We're gonna solve you later. Anyway, my point being, ignoring my problems with whatever I'm having, here's a definition for a VPC. Here's a definition of an internet gateway. Here's us attaching the internet gateway. Here's the public subnet definition that we're defining. In other words, each of these things listed under resources, these are objects that are created inside of our account. This is all defined in a file. This file is submitted to the CloudFormation engine, the service, and then it asks me any questions. So if I have any questions, they're called parameters, by the way. If it has any questions to ask me, it asks me questions. And if I answer the questions and then say go, it then builds all of these resources. Notice there's a lab security group here. Here's an instance D. I don't know why they call it instance D, but whatever. And then, so it's actually creating a instance, and it looks like it's based on an Amazon Linux ID. And it looks like it's downloading some kind of data zip file. And so this whole file is a CloudFormation file. Notice there's an output section here that's just going to show me things at the end. If I kick this into CloudFormation, CloudFormation is going to basically create a stack, a resource stack that has all these components in it. If I make changes to the stack, I can actually detect any drift or any kind of deviation just by running drift detection on there. So, you know, that's an example of one that creates an EC2 instance with networking. Here's another one, and all this one does is it just starts an EC2 instance. It's the only thing in there. Now it does require the existence of the networking pieces that it's looking for. Like for example, this has to already exist. But these CloudFormation files can get huge. I've got a Jenkins one that's like 10 pages long. Never do that again. But you know, now we would just use Terraform or something along those lines to do it. But CloudFormation is the native infrastructure as code tool for AWS. So even if you write in Terraform, you do actually need to know a little CloudFormation in order to like be good at it. Same with Pulumi. So this is what infrastructure as code means, is because I can take this file that we were just looking at and I can put this in a code repository. And as I make changes to it, I can just add versions to it. I can version it as part of being a code repository. I could add a version number. This thing can be shared and tested with other people. So the file gets submitted to the CloudFormation engine that creates the stack, the resource stack or architecture stack, and then resources are created. CloudFormation doesn't cost anything. All that's required is that, you know, you have to have a file, but anything it creates, it's going to cost you something, but using it's not going to cost you anything. Now, the benefit of this is that now I can give this to people and we can all have the same setup and same environment, right? And not only that, but typically like the networking team and the security team and, you know, the, let's say hosting or, you know, infrastructure team can all create their own stacks, and then developers can just put their stacks on top of those stacks. So you can actually refer to other people's stacks. The only thing you need to do is just tell the people above you what the reference number is for your stack. So this allows your templates to not only be reusable, but other teams can now know that they're going to get consistent infrastructure from you as well. Also, if you do this, by the way, you can create a service catalog and share this out as almost like a vending machine where people can go and get EC2 instances that are built the same way every single time. That includes compliance, agents, backups, the whole 9 yards. If you update a stack, by the way, with a new security group and you like resubmit it, it will update only the things that have changed. So unless you've deleted the entire file, it's going to follow the same kind of rule set. So CloudFormation, like I said, is based on templates. They're submitted to the CloudFormation engine that creates the assets. That set of assets is called a stack. It's a stack of resources. Now, a CloudFormation template has a few key pieces, but the one that is the most required is that you have to have some resources, because resources are what you create inside of AWS. No resources, well, then there's nothing there. There's no reason to create anything. Note that this can be in JSON or in YAML. So unlike Terraform, which is in HashiCorp's proprietary language, or JSON. So either one works fine, just as long as you are syntactically correct. And then the stacks that are created could be comprised of anything. CloudFormation pretty much supports almost every single service, except for like new services and their features. You can create change sets where you can make a change to a template for an already existing stack and then see what the differences are. CloudFormation will tell you what it's going to change. And you can say, look, I want you to implement the change set. So note again that templates are required. No, sorry, resources are required. So, pardon me just 1 second. Sorry, everything went weird for a second. So just know that resources are required because that's what you're going to build. But you have sections like transform, outputs, mappings, conditionals. Really all you need is, I believe, the template format version and the resources. That's it. Metadata, parameters, mappings, conditions, transforms, and outputs are all optional. And they all do different things, but resources is required. Now, as I mentioned before, you could have one team handling identity. And so they're focused on, for, as an example, this stack down here. And then this stack is used by the networking team because they need references to, set up users or refer to users to get permissions or whatnot. And then maybe this is like subnets and security groups. Maybe there's a security piece here, right? Maybe this is where your databases and any kind of other analytics are set. And then maybe this is where the front end goes. So you can have stacks referring to stacks inside of CloudFormation. So you can have a layered kind of team approach to how you use CloudFormation. Now, hold on just 1 second. Things are getting a little weird here. There we go. So pre-built reference architectures. So the AWS solutions team basically has a couple of reference architectures that you can find. Oh God, what is the URL for that? Is that right? I love it. That I would actually remember that. That's weird. So this is one of the URLs for the solutions implementation. This is a great place, by the way, if you're like, hey, I would like to find a reference deployment for Kubernetes, because I hear Kubernetes is cool, right? So you could find it down here. If you're looking for EKS, by the way, which is Amazon, there's a reference architecture. When you click on these, there's literally a deployment guide. And if you click into it, you can actually quick start into the console. So you could like deploy into a new VPC if you wanted to. Now, I don't think currently I'm logged into an account, so this is probably going to fail. But this would literally open up inside of your AWS account if you were logged in. Oh, you can actually add this to service catalog. That's a new button that wasn't there before. So you can actually add this as an option into your service catalog so that other people, like a vending machine, can consume it. That's pretty cool, actually. So just know, how do we get so far ahead? Pardon me, just 1 second. Obviously, I'm having some problems. Just know that the solutions implementation link that I posted will give you access to that whole cadre. It's like a library of CloudFormation templates and deployment guides. Very useful for accelerating and deploying in new technology. There's probably quite a few in there, ranging from the most popular technologies from Oracle, typical, whatever enterprise software you're using. So it's a great way, certainly, to kick the tires or learn more about how to run that software in your account. And you can use those CloudFormation templates as a base template that you can modify for your own environment. Now, I would be totally remiss if I didn't mention the Cloud Development Kit. Now, this is going to have a one-pager on it. If you're interested in learning more, there's a workshop that Amazon's published called the CDK Workshop. And this will allow you to practice writing in the CloudFormation Cloud Development Kit in your favorite language that you have. Hopefully it's over here, if not. But like Python, for example, and it will basically walk you through using your own personal account, using the Cloud Development Kit to do things like deploying a Lambda, hitting an API gateway, setting up a counter, all inside of CloudFormation. And so if you look, let's see. This will set you how to use Python, and then let's look at the Hello CDK, and it will help you see the languages, right? So it'll teach you how to write in Python to create your own CloudFormation infrastructure, your AWS infrastructure. TypeScript, Python, Java, and .NET are the applications that it currently supports. This will probably cost you less than 10 cents, if that, as long as you don't leave anything running if you run this in your own account. So just know that's there. So the Cloud Development Kit basically is an importable library that allows you to use any supported language to create all of your objects inside AWS. It automatically submits your template and does your CloudFormation submission and then creates the stack. So it converts everything you write into a CloudFormation template, which gets submitted. It's pretty cool. So CloudFormation and the CDK is like a program enhancement to CloudFormation where you can just use your favorite language to write your CloudFormation files. Okay, so that's CloudFormation, which is basically just a file-based way to define your infrastructure using the proprietary language that AWS wrote for CloudFormation. It's in YAML or JSON as far as syntax goes. The CDK, again, favorite programming language. Now, as we move past this, then we have to talk about Systems Manager. So CloudFormation is used for provisioning infrastructure. Systems Manager is used for managing that infrastructure once it's up and running. So how do we get inventory? How do we patch? How do we set baselines? How do we manage operational challenges? So Systems Manager will do some provisioning, lots of configuration management, operation and compliance management, and it'll do monitoring. So it's got 17 subservices underneath it, including Patch Manager, maintenance windows, inventory, automation, Ops Center. It's got all this stuff, personal health dashboard. So Systems Manager has a lot of benefits. Notice that these are all the things that are there, including app config, the parameter store. Distributor is new. Didn't even know distributor. Oh, that's a software distributor. Actually, I didn't know that was there. Session Manager. So if you don't want to create a jump box, you can use Session Manager to log in through the AWS console into your boxes. You can run one-off commands with the run command, or you can use the automation system in order to run commands that repeatedly base off of different triggers and events. Systems Manager is the heart of the systems operations class on AWS. So if you want to know more about it, architecting class is not really the place to learn about it because it's a systems admin function for the most part. So systems operation that on AWS, that class goes into detail on most of this, not all of it, but most of it. Just know that Systems Manager's function is to manage fleets of systems, including some of the associated services. That's it. Questions of any type? Cool. All right, so then let's take a little challenge here. What is a CloudFormation stack? What is the stack in CloudFormation? What is it? What is that exactly? A, B, C, or D? Yeah, stack is nothing more than the resources generated by a template. So good, Alex. Yeah. So that's all it is. A stack is just a collection of resources that were created by CloudFormation. All right. Which section is required in a CloudFormation template? Which one did I say was required? Which one did you see? Yeah, resources. You got to create something. So that's required. So that's it right there. Good. Good answer, Alex. Thank you. Okay. Which of the following are benefits of using CDK with CloudFormation? We didn't really talk about this, did we? Definitely A, that's one of them. Developers can use known languages instead of having to learn CloudFormation's proprietary language. Let's see. Other answers. Using a CDK does not require an AWS account or credentials. Unfortunately, that's not true because you can't access AWS without using credentials. But one thing that is true is that developers can call pre-configured resources with proven defaults. That's not something I would expect you to get because we didn't really talk in detail about that. But it allows you to like reuse the same object calls using the same parameters. So it allows you to use the functions of a programming language to like call pre-configured resources, right? So proven defaults also means that there'll be some best practices in there applied as by virtue of using the CDK. Okay. Just one thing to be aware of, because we're at the end of the module. Is that there are tons of really good CloudFormation templates out there. If you go to github.com, and in particular, Amazon has some great CloudFormation templates under CloudFormation AWS Labs, which is their official kind of site. If you look under here and ignore the community pieces, I wouldn't touch those. If you go to AWS, don't get me wrong, the community ones are actually okay. You just have to read them. You can't just pull them down and use them because they weren't written by AWS. Now AWS checks them, but you know, what if they miss something? Now for the AWS ones, they get parsed. So let's say that you're like, I want to start using a service and I'm really interested in learning how to use, where is it? Elastic Container Service. Here, by the way, are actual CloudFormation templates that like have both the EC2 launch type and the Fargate launch type. You could click into this, come in and grab a cluster, right? And you could actually literally look at it first and say, what is this thing doing actually? Well, it's configuring a subnet. Here's the VPC. It's creating another subnet. Here's another subnet. Here's an internet gateway and some route tables and some routes that are being added. Here's some associations, which is awesome. We need that. And then here's the definition of a cluster. And then there's a container security group, an ECS ingress for a load balancer, and then a security ingress from self. And then here they're creating a load balancer and ooh, looks like this public load balancer security group, public load balancer. Here's a dummy target public group. And then a listener for the load balancer. So you can actually see, and then here's a role for ECS. So this is all a file that you can just grab for free off of GitHub from AWS Labs in particular. Be careful about what you pull down. If you pull out somebody else's repo that you don't know, please read it in its entirety. And then here's some outputs. So if you load this up, this is going to actually create an ECS cluster for you and set up, some Fargate configuration for you as well. So just know there's tons of great resources out there for CloudFormation. Okay, that's the end of module 8. Now we're moving on to module 9 on containers. Does anyone have any questions about anything related to CloudFormation, Systems Manager, the Cloud Development Kit? Hey, there's my Kindle library. There's my email. All right. Okay, this is going to be fun because we're going to talk about containers. Now, if you haven't touched containers yet, I just got to tell you, it's kind of taking the world by storm. I hate saying that because I hate hype cycles. I really just abhor them. But I fought it for a long time. And then a couple of years back, I started doing containerized deployments. And I got to say that now pretty much everyone's doing containers. It's just like, ugh. And there are pros and cons, nothing's a panacea, but containers actually add a tremendous amount of benefit, especially from the development to production deployment cycle. So just know that if you're not using containers, you will be. Doesn't matter if you're a data scientist or what your role is. It flipped, and I think like 65% of the major tech giants are all using containers to deploy into production. Companies like Google have been doing 100% for years. So take that as you see fit. All right, let's check in then. All right, so someone answer this for me because I haven't even asked. What percentage of travelers' workloads run on containers? Does anybody know? Does anybody who can hear my voice have any workloads that are running on containers? Cool. The strategy is in flux here. Well said, Erica. That was well done. I like that. You should come with me. We can go do digital transformation together. That's a very consulting statement. So the strategy in flux here. All right. So yeah. So, oh yeah. Is that what's happening now, Alex? Are you just throwing out words related to containers, or are you actually using OpenShift?
Yeah, at least in Canada, we only use OpenShift. We are not allowed yet to use ECS or EKS. It hasn't been blessed yet.
Okay.
It's going to get there, but because OpenShift is now not the way to go, even though it was the way to go 2 months ago. So everything's in flux.
Oh, that's
Erica said, yeah, everything keeps changing. The moment you know that it's there, it changes again.
huh.
So, yeah.
That's interesting.
That's where our containers are right now, OpenShift.
Good. And now Erica's reflecting back to me. She's like, that's why I said it's in flux, Forrester. Well, that's interesting because most companies actually start with OpenShift, but they don't stay with OpenShift. So when I got to Honeywell back in 2018, as their like global architect for cloud and containers, they also were on OpenShift. And, I worked for Red Hat on OpenShift last year, and just between you and me, I left. But like, they had a great strategy. And I think that what they do with Kubernetes and OpenShift is great for people who are new to the product. And OpenShift is a first-class citizen on AWS, Google, and Azure. So, as a managed service offering, it is available on all 3 platforms. The only problem is that OpenShift brings a lot of pre-configured opinions to the equation. So I can see why the strategy would be in flux. It's a great place to start. I'm surprised you guys didn't stay with it, but most people will evolve away from it towards either a plain standard Kubernetes distribution or use one of the managed service providers because it's just so easy to use a managed service provider. So containers on AWS in particular are super easy, particularly if you're not using Kubernetes. But if you are, it's still a sweet way to run Kubernetes, which OpenShift is just Kubernetes and a bunch of extra stuff thrown on top. So good to know, actually. Less than 10%. Okay, so here's what we want to talk about around containers. Notice it says stakeholder feedback is compute. That doesn't sound right. Slide 5. Hold on one second. Okay, so currently only 27% of our workloads run on containers. That is a very specific number, by the way. We expect the percentage to double. Over 90% are Docker with a growing number of Kubernetes-based applications. Huh? Anyway, just so you know, by the way, you're not going to run Docker in production. You're going to run Kubernetes in production. So that's a really confusing statement, actually. Hold on. So why? Because Kubernetes will run Docker containers, just so you know. So that's why I'm confused by that statement. All right, so at the core of our container expansion is the fact that we have 68 legacy applications ready to be re-architected into containers. Interesting. We might be doing a microservices expansion. So although we won't be working with application code, everyone needs to understand the significance of microservices and containers for modern application development, because no one wants to be legacy. It's uncool to be legacy now. So we need to know what AWS services are available for our container deployments. That we can get behind. So then here's the objectives. When is it better to use containers for compute needs? What solutions do we have to ensure apps are highly available and scalable? How can we build an application agnostic, an infrastructure agnostic environment for applications? So here we've got app servers. Are those containerized apps? Like, are they containerized apps? Are they servers that are running Kubernetes? I think we're going to find out. Let's, by the way, presuppose that this is an Elastic Container Service cluster in a private application subnet. Let's just presuppose that for a second. Now, this is a great card, by the way. My manager told me we should use microservices, but I don't know why. Let's pause for that for a second. I know none of you have never heard that. All right. First of all, why is everyone so hot on this like architectural pattern known as microservices? Just so you're aware, I worked for ThoughtWorks last year, worked with a gentleman named Martin Fowler. He was one of the signatories for the Agile Manifesto, and he is one of the greatest proponents and detractors of microservices I've ever seen. If you really want to understand microservices and all the like ins and outs and challenges, Martin Fowler has a great section of his website about microservices, including when not to use them and when to use them. So we're going to talk about some of those kind of ins and outs, those patterns and anti-patterns. But the main thing you should know is that the reason people are looking at microservices is because it pushes us towards cloud native style of development with small batches and services that are isolated from each other, that can scale independently, but yet talk through APIs. So there's really three characteristics of a microservice. One, is it made up of multiple independent services that can scale and deploy independently? And do they talk to each other across the network through APIs, like a standard interface? That's really what makes a microservice, is it an independent business process? Is it independently scalable and deployable? And is it talking to other services that make up the entire product through APIs? If it is, it's probably a microservice. So part of that emphasis is that we want applications that are loosely coupled versus tightly coupled. That way, if a component fails, we can fail gracefully or we can keep on going. I'll give you an example of this, by the way. This is risky. Why? Not because I'm just being silly. Where are you? Oh, there you are. All right, let's say we go to Netflix. This is where it gets risky, right? I'm just kidding. All right, so let's say I'm here and I'm on Netflix. Now, this whole website is a presentation microservice. All it does is aggregate data from other services and present this into a web page. That's it. Now, so there's a microservice that's handling presentation. There's another microservice that's handling things like my account management. And maybe billing, by the way, is actually being handled differently here as well. There's another microservice or series of microservices that's handling release in the past year, trending now, continue watching, futuristic sci-fi, like top 10. These are all independent services that are managing their own data. And the presentation service is actually just gathering this data and presenting it up. Tell me what happens if all of a sudden I can't get like my list. What's going to happen to this web page? Can someone tell me? If the presentation service can't talk to the my list service?
They're like empty windows. But
Say again, Alex.
they become like gray windows, like you can't actually see it. But then it may appear like a few seconds later.
Actually, in my experience, what happens is that it doesn't show my list. And if I refresh the page and the service is working, all of a sudden my list shows up. So it actually fails gracefully by not showing the data, because I don't necessarily get freaked out because I'm not seeing, I'm like, where's my list at? And I'll scroll down and all of a sudden it'll load up, right? So what happens is that if these independent services fail, the presentation layer is just like, well, I'm not going to present your data. If the user refreshes and the service is available, it comes right back, no issue. But I would never actually know that the service would fail. It just doesn't, the presentation layer doesn't present data from that service. So this is interesting because this is all very loosely coupled. This is a web page that has 20 components on it. And if one of the components fails, it doesn't display that the component failed. It just moves on to another component. That's the very definition of loosely coupled, because these services, if they fail, they don't interfere with the actual presentation of the page. Now, if I'm a customer and I'm like, hey, where's my watch it again section? I scroll down and I don't see watch it again. I might hit F5 and guess what? It refreshes the page and I'll be like, hey, oh, there it is. Hey, guess the service is working now. But it's not going to display an error. It's loosely coupled, so it's just going to like not display it because that's graceful failure. That's what doing something like having loose coupling allows for. If that web page was completely dependent on the presentation of my list, then it would throw an error. I would see that error and the customer experience would be impacted. Now that's a front end example, but you can do that with the back end as well. What if, for example, if you go to access the caching server, it's not there. I don't need to throw an error to the user. I can just go to the database and get the data. In other words, you really want to think about how your application is going to fail and what that graceful failure looks like to the customer. And of course, how it gets surfaced to the backend people who are going to fix it, obviously. So best practice is try to keep things loosely coupled. Don't do this, for example, where you actually tell the web servers the number of application servers that are on the back end. Don't do that. Put an abstraction point in there. An internal load balancer could act as your abstraction point so that all the web servers talk to that internal load balancer. And the web servers don't care if you've got one application server or 50 behind the load balancer, as long as the web servers can get their data when they need it. We do this all the time, by the way, websites. If I go to Amazon.com, you're actually not hitting a server. You're hitting a load balancer that is feeding out to 50 to 100 to 1,000 servers. But I'm actually hitting the load balancer. If that load balancer doesn't have a server to talk to, that's the only time I'm actually going to see an error. But when is that going to happen? There's 500 servers on the back end. One of them is not going to be able to take my request. So putting load balancers, also known as abstraction layers, is a great way to decouple things. It allows you basically to have a staging point between one connected entity to another connected entity. In this case, web servers to application servers. Now, other things to note. When we talk about using a microservices pattern, what we're doing is we're taking what would have traditionally been one application with one code base, and we're splitting it into 3 applications with 3 different code bases, and it scales independently. So each of these runs as a service. If I am running a special and all of a sudden I got a bunch of hot topics and I need to expand this, I can add more topics without having to necessarily scale users or scale messages. In other words, I could scale topics out, but I can leave users and messages at the same level. In a monolithic application over here, if topics became overloaded, I'd have to scale this whole thing as many times as was needed to get topics to work. But meanwhile, I am uselessly running user and messaging code that I don't need. Now, is that a big enough problem for you to go for the complexity of microservices? That's your call. But in general, the trend is towards microservices, independently API coupled services that talk to each other through APIs. Now, when you architect for microservices, one thing to note is that you might have different endpoints or different sections of your website that actually go to different servers depending on what they're trying to do. So in this case, let's say it's an API driven application. If someone goes to example.com, but they go to users, they go to a different set of servers. If they come over here and they go to example.com and they go to topics, they go to another set of servers. And obviously, just to repeat that, if they go to example.com and they're going to messages, they go to a different set of servers. These systems over here are all running different applications. They are scaled independently. And if they need to talk to other services, they're going to use an API to talk to the other systems. Now, actually, what they'll do is they'll probably come out here and then come back in here. But regardless, that's a little more complication than anybody needs. But these services are going to talk to each other, right? Now, is that tightly coupled? Yes. So again, most likely what they're going to do is they're going to come out here and then come back in this way, right? Because then that way they can hit whatever scaling is going on. They're not going to go direct. Now, microservices don't follow a one-size-fits-all approach. So for example, one of your microservices could be written in Ruby and could be running in Lambda. Another one of your microservices could be written in Python and could be over here running on EC2. Another one of your services could be written in Java and running on an ECS cluster. You don't care. As long as these guys are all talking using the same programming interface, you don't care. Like, they know how to talk to each other. It doesn't really matter. You can write it in any language you want, as long as there's a published API that they can use to speak to each other. So microservices, and let me actually pull that up because I think that might be very useful. I know it's the end of the day, but you can probably take a look at it at some point in time. Let's see, Martin Fowler, microservices. So Martin's got a bunch of great articles. If you really want to peel this out and you work as an architect or even a developer who's having to deal with this, he's got some really great content about characteristics of a microservice architecture. I like this. Are microservices the future? Right? Just some thought pieces to really consider. Okay. So that just talks about loose coupling, and a microservices design pattern has kind of like the way that a lot of cloud applications are focused on. The reason this is done in the context of containerization is because containerization goes with microservices like peanut butter and chocolate. They're both good separately. I mean, I love a good spoonful of peanut butter by itself, but when you put it together, it becomes something special. Although Reese's peanut butter cups are awesome, but man, I wish they would use like fresh peanut butter. That stuff is disgusting. Anyway, moving on past my little peccadillos around candy. So X-ray is what you would use to actually monitor end to end, either a virtual machine hosted application, a container application. I don't think, oh, you can turn on, actually, you can turn it on with Lambda. That's a recent thing, actually. You can actually get Lambda to be part of your X-ray profile. X-ray is used to debug applications, and it makes this beautiful service map. So you can actually see all the stages of your AWS services and where they're succeeding and where they're failing, and how long they're taking and what the error rates are. It's actually a pretty cool app. So X-ray helps you basically debug and analyze your modern applications all the way through serverless to microservice architectures. So it's really cool. You access these things called traces, which basically allow you to see what's going on. You can also do segments and subsegments. A trace is kind of like an end-to-end kind of piece that allows you to troubleshoot a user's journey through your services. So super useful. This is actually part of a larger project that isn't just AWS specific, called Open Tracing. And Jaeger is the open source component that does this. But X-ray has a very slick and sophisticated integration with AWS. So it's a good product to use when you need to troubleshoot. Okay. Now that's a bunch of stuff about microservices and how to troubleshoot. Let's talk about containers. Okay. So one question that comes up is like, what's the difference between a container and a virtual machine? So someone explain that to me. Does anyone know what the difference is between a container and a virtual machine is? It's not really easy to explain, actually. Anyone want to take a shot at it?
A container will shares the host kernel, the operating system of the host. So every container will actually share, that same operating system. Think of VM is like an entire machine, like everything down to the almost not quite the hardware, but pretty much like an image of the entire, Linux box or Microsoft box. So it's kind of virtualizing the hardware, whereas containers are kind of virtualizing the operating system in a way. So yeah, it's hard to explain, but containers are a lot more lightweight than virtual machines.
Yeah, like I said, I'm gonna have to mark the date, November 16th, 3 days before my birthday. You are the first student in the history of me teaching containers who has actually said that properly. That's pretty amazing, honestly. Like you really are. Like you're the first one who's actually noted that containers are not virtual machines. They are not running a kernel, whereas virtual machines are virtualizing all the hardware, right? You also said that containers were lightweight. That's absolutely true. Containers are lightweight because they don't have an operating system inside of them. Now, don't get me wrong. You can copy all the files of an operating system in a container if you want to, but you were dead on, Alex. Typically, we don't do that. We just copy a process, like an application in there, and we run containers, and that's it. That's all it is. So the simplest way that I usually say this, and it does require like the explanation that you gave, Alex, is that a container is application virtualization. You're just taking a Java app or a Python app, you're taking that application and you are sticking it into a packaged format. If it was a virtual machine, you're taking an operating system plus any applications and you're sticking that into a packageable format because that's what we have AMIs for. That's what we have, what do they call them? VMDKs, like the VMware disk images, right? That's what we have those for, is because those are just snapshots of an operating system. A container only has the process typically. A virtual machine has the entire operating system plus the process. So that was well done, actually. I got to note that. That's the first time anyone's ever said that properly. So that's good. Because, to say this is that containers basically are trying to solve this problem. When we deployed applications before, if it's a Python app or a Java app or .NET, they're all kind of weird. Like they're packaged differently. They use different packaging frameworks. So it's like a little bit like running a shipping container. Like you're running a boat and someone gives you bananas, monkeys, and tires. But they're all just in bags and the monkeys are, in a cage. And you're like, where? How am I supposed to stack this thing? Because you really can't. And so you have to have different ways of dealing with the bananas, the monkeys, and the tires. Well, and what happens is that with containerization, which Docker, by the way, is just a flavor of containerization. They are the ones, by the way, who made it popular. So like saying Kleenex is a tissue, right? What happened is they took these processes and said, look, if I got Java, Python, Ruby, .NET, why don't I just put it in a standard packaging format? And as long as I have the cranes, the ships, and the trucks that can handle a shipping container, then I can handle the monkeys and the tires and the whatever, because they're in these square boxes, these rectangular boxes. By the way, it was 1958 when the shipping container was standardized, right? So here we are, 2013, 2014, Docker comes out and says, hey, what if we just put all of our applications, whether it was Java, Python, or whatever, and everything they needed into a standard package format? And if you have the software to run this standard package format and you match the operating system, which was Alex's point, you can't run a Windows container on a Linux box. You can't run a Linux container on a Windows host, right? As long as the processor architecture and the operating system match, then I can pull that container down, I can run it. So that makes it look like this, because now I can stack multiple containers onto a virtual machine and get a lot more density. And I don't have to worry about the monkeys and the bananas and the tires all stepping on each other's toes, right? I don't have to worry about the monkeys breaking out and eating the bananas, right? I don't have to worry about that. That's what containers do, is they isolate processes so they don't interfere with each other. So containers are repeatable. They are self-contained process environments. They take seconds usually to spin up. It depends on your application, but on average, they are portable. So if I make a container image with Java in it, and I put it up on hub.docker.com, which is a registry for containers, and I give that URL to Patrick's, any of the Patrick's, then what will happen is I can then download and run that container, no issue. So just know that dependencies, the runtime engine, environmental consistency, all the code, it's all packaged in there. So I can just literally pull it down and go. Again, remember, you have to match, if it's a binary, like piece of code in particular, like it's been compiled as a binary, it has to match what the binary was compiled for. If the binary was compiled for Windows, you need to be on a Windows host for that container. If it was compiled for Linux, x86, you're gonna have to be on an x86 Linux box to run that. By the way, Windows usually gets around this by running a virtual machine to host your Docker containers that has Linux inside of it. So that's why you can download Linux containers all day long. Most containerization is about Linux-based systems. It's not about Windows. Don't get me wrong, Microsoft has had containers since Windows Server 2019, but the container ecosystem on Windows is slightly different, and that's not what most people are talking about when they talk about Kubernetes and whatnot. Again, Kubernetes supports Windows hosts, but just know that mainly we're talking about Linux. The Windows ecosystem for containers is not quite as mature yet. It's close. So then why, Michael, did you say that containers and microservices go together like peanut butter and chocolate? Well, because if you're going to fragment your code base into 15 different independent services and make them smaller, well, guess what? Containers are smaller. So that's perfect, right? So it's a great kind of combination. Now, take a guess at this. What's the cost of splitting all of your code into more services? What's the cost of that? Someone speculate for me and tell me what the cost is there. Does somebody talk?
It depends, right?
Well, there's one consistent cost to splitting a large code base into smaller microservices.
All the services, all the containers have to talk to each other. So the whole application becomes kind of chatty.
It does definitely require more network bandwidth. Doesn't necessarily mean that latency is worse. Although to Patrick's point, to Mr. Skiba's point, it is true that memory is faster than networking. So maybe some higher latency, but that might not be an issue. But what, like if all of a sudden I had 3 applications on the left and I've got 20 on the right, what did I just do to myself?
Well, you have 20 deployments versus 3. You're looking at that.
Well, yeah. So all of a sudden you now made things more complex, right? So just to be aware, we've now
trade-off, though,
made,
right?
wait, sorry, go ahead. What'd you say, Patrick?
It's a trade-off right now too. When you look at the ease of, like, you know, the maintainability. So instead of having like this huge like application, you know, where you have like all the code, now you have it spread out. So when you look at future state for like maintainability, it's easier to work on like one small application than trying to dig through legacy code.
Oh, totally agreed. I was just talking about what the cons were. There's a ton of
Oh.
pros. Yeah. Yeah. The con is that things have now gotten complex, right? The reason I mentioned that is that this is why the Elastic Container Service and the Elastic Kubernetes Service exist, because I went from managing 3 applications that were larger to now what, 50, it's usually a microservice is about 15 to 20 applications. services. So now I've got far more applications to manage. You're right. I get independence, independent deployability, independent scalability. I get more efficiency, but I've now added complexity to my environment. How does that complexity get offset? And I mention that because that's why AWS and others like OpenShift exist, because they're trying to reduce the complexity cost by giving you a system that will manage the distribution, the health, and the monitoring of these now spread out services for you. That's the only kind of really like downside of running containers in production, is that you've now added complexity to the equation. So who's going to manage that complexity? Usually that falls on operations, but that's why Kubernetes and these other software services that have come out are so popular, because they help you solve that problem. That was the whole point in sharing that. By the way, here's another visual around how apps sit on bare metal services versus, right, virtual machines, which notice there's a guest OS here, right? And then over here, there's no guest OS. So if we go over here, there's no guest OS. It's just the apps. But the thing that's not shown here is that these containers are isolated from each other. They're completely isolated. Notice also that there is a containerization software versus the virtualization platform. By the way, that this server hardware could be a virtual machine, which oftentimes it is. So don't be fooled. Virtual machines are still in play in a cloud environment when you run containers. Now, if you run the serverless version, obviously you don't see the virtual machines, but they're still there. So you still require an operating system to run containers. You still require either a virtual machine or hardware. You're just not managing those pieces. That's it. Okay. There's a couple other things that we need to cover. Let me cover these last two slides and then we're going to stop because it's like 5 o'clock, right? So the last thing to note here is that notice that in order for you to be able to run containers, you need some kind of containerization software. Here it's listing the Docker engine. I'll be frank, most of us are not going to do that in production. We're going to run Kubernetes or some other kind of containerization software. You're not going to run Docker in production. I know that sounds weird. Unless you're running Docker Swarm, which is different than Docker, really. It's an orchestrator, just like Kubernetes. But you're not going to run the stuff that you run on your laptop. You're not going to run that in production, just FYI. So just know, though, that, again, notice the size. Containers just has the apps and the libraries. There is no guest operating system like there is over here. So just driving home that point. We're going to talk about, well, we might talk about EKS in depth if time is available. But the main thing for you all to know in 2021 is that if you're running containers in production, you're going to be running either Kubernetes or you're going to be running a proprietary service like ECS to get your containers managed. So that's the main thing to remember about all of this. Let's see. I think there's one more slide. Yeah, man, that is so misleading. I don't know why they're doing that. This, by the way, should say Kubernetes. You are not going to run a distributed Docker system in production. So just want to make sure that's super clear. This is a nice little drawing, but you're not going to do a distributed Docker system. You're going to do a distributed Kubernetes system. It's very different. So yeah, you could use Docker Swarm, but honestly, Docker Swarm has fallen out of favor and Kubernetes is the default industry system for this. So just remember, the main thing here is that these containers are independent and isolated from each other, and they can get distributed across a whole host of systems, but you need a piece of software to do that for you because you're not going to do it manually. Okay. Our next conversation is actually going to be about container services, and that will actually end this slide deck, but it's 5:02 and you have been champs. We probably got like 10 or 15 more minutes left. And so we're pretty much on track for tomorrow. So when we meet tomorrow at 9 a.m., I'm going to go through this last little piece and then we're going to run through the day. Remember, get your coffee or whatever. Make sure you eat a pretty like light lunch because you're going to have a 2-hour, 90-minute lab at the end of the day. That's going to be your capstone lab for closing out the course. So just be aware that there's going to be a sprint at the end of our class. Okay. Any questions for me before we close for the day? All right. We will see you all tomorrow. Looking forward to it. See you at 9 a.m. Eastern.